Okay, Leanne, I think we can go ahead and get started if you're ready.
Yes, I am ready.
Okay, good morning. I'm Aaron Yao. I'm the designated federal officer for the Clean Air Scientific Advisory Committee. In my role as DFO, I'd like to formally open this public meeting. The CASAC is an independent expert federal advisory committee chartered under the authority of the Federal Advisory Committee Act. The CASAC is empowered under the Clean Air Act to provide independent advice to the EPA administrator on the scientific and technical bases for EPA's National Ambient Air Quality Standards. FACA and EPA policy require that CASAC meetings be announced to the public in the Federal Register and that substantive deliberations and interactions with EPA and the public be conducted in open sessions where DFO is present to ensure that the requirements of FACA are met. The purpose of today's meeting is for the panel to receive a briefing from EPA on the policy assessment for the oxides of nitrogen, oxides of sulfur, and particulate matter secondary NAAQS. The panel will meet again on June 28th to 29th in North Carolina to peer review the PA, and public comments will take place during that meeting on June 28th. For further details, please refer to the Federal Register notice announcing the meeting. Minutes will be prepared to summarize discussions and action items in accordance with the requirements of FACA. I will work with the chair to certify the minutes and have them posted on the CASAC website. The CASAC consists of special government employees appointed by EPA to their positions. As government employees, the members are subject to all applicable ethics laws and implementing regulations. The SAB staff office has determined that advisors participating in this meeting have no financial conflicts of interest or appearance of a loss of impartiality under federal ethics regulations relating to the topic of this meeting. To those watching the live video webcast, please send me an email indicating your attendance. If you had previously requested a call-in number, you do not need to email me again. I would now like to turn the meeting over to Dr. Leanne Shepard, Chair of the CASAC.
Hello, everyone, and welcome to this meeting of the CASAC for the, as Aaron said, for the NOx, SOx, and PM secondary standards review. Our purpose today, as Aaron mentioned, is to receive a briefing from EPA about the policy assessment. This will prepare us for our meeting in June. As a member of a CASAC panel, I aspire to the following goals. One is to provide useful advice to EPA with a focus on whether the document is adequate for the intended purpose. Another is to engage in collegial give and take discussion of the charge questions, and finally to reach consensus if it is at all possible. So after we go through panel introductions, I will turn the meeting over to EPA. Regarding the panel introductions, I'll invite each panelist to introduce themselves in the alphabetical order as listed on the roster. And I ask the panelists to turn your video on for the introductions. So first of all, I'm Leanne Shepard, Roman Haas professor in public health sciences with appointments in both environmental and occupational health sciences and biostatistics at the University of Washington. And as a biostatistician, my expertise is in modeling exposure and understanding the implications of those modeled exposures for inference about health effects. So now I invite Dr. Praveen Amar to introduce yourself.
Good morning, everyone. Can you hear me?
Yes.
Yeah. Oh, wonderful. I'm Praveen Amar. I am now currently semi-retired, but I worked for a long time with NESCOM, working with state governments on these issues, and then also Clean Air Task Force. And after that, currently working as an advisor, a science advisor to the state of New York, NYSERDA, on issues of climate change, air quality, modeling, emissions, health effects, the whole works. And I have been on this CASAC panel right from the beginning. I think it was 2008, the first effort, which ended around 2011 or 12. Then second effort, which kind of started, and now it's kind of restarting, I think. So I'm pretty fuzzy about, I was looking at all the material we had worked on over the years. So I'm looking forward to what EP has to say. Thank you.
Thank you very much. And thanks for that historical perspective as well. Jim Boylan.
Yes, hi, everyone. I am Jim Boylan, Chief of the Air Protection Branch at the Georgia Environmental Protection Division. My background is in NAAQS implementation, including ambient monitoring, emission inventory development, air quality modeling, permitting, and control strategy development. Thank you.
Great. Thank you. Next is Douglas Burns. Is Doug here? Okay, we'll move on to Lorraine Chestnut.
Hi, I'm Laurie Chestnut, an economist. I specialize in environmental and natural resource economics, and particularly the valuation of non-market benefits of environmental regulations. I'm retired at this point. I worked for many years as a consultant with Stratus Consulting, and did a lot of work for EPA on benefit cost analysis of regulatory analysis of environmental regulations. And I served on this panel previously as well with Praveen. So thanks.
Great, thank you. Next up is Judy Chow.
Hi, I'm Judy Chow, a research professor in the Division of Atmospheric Science of Desert Research Institute. We're part of Nevada System of Higher Education. My research interest has been on air quality monitoring, network design, gas and particle sampling, chemical analysis, data analysis, and the receptor modeling, source apportionment. Thank you.
Thank you, Judy. Next up is Charles Driscoll.
Good morning, I'm Charlie Driscoll. I'm a professor in the Department of Civil and Environmental Engineering at Syracuse University. I have interests in ecosystem impacts of air pollution, climate change, and I have served on this committee previously as well.
Great, thank you. Next is Ivan Fernandez.
Good morning. Ivan Fernandez from the University of Maine, the School of Forest Resources and the Climate Change Institute. I'm a soil scientist, biogeochemist. I've served on this panel in the past, and my research has dealt a lot with air pollution and ecosystems, and I'm involved a lot in the state of Maine, the Climate Council, as well as chairing the science committees that support the council work in the state of Maine at present. Thanks.
Great. Thank you. Next is Frank Gilliam.
Yes, I'm Frank Gilliam. I also served on this committee through the years. Actually, it's good to see a lot of familiar faces. Most of the work that I did that's relevant to the work we're doing was done when I was in West Virginia at Marshall University for about 28 years. I left that to allow my wife to take a position here in Pensacola, Florida. I'm currently on the faculty at University of West Florida. And most of my areas of interest were the effects of excess nitrogen on montane forest ecosystems. Thank you.
Thank you. David Hens.
Hi, my name is Davin Hensley, and I'm a professor in the Department of Mechanical Engineering at the University of Colorado in Boulder. And my research interests are the fate and transport, as well as the sources of air pollutants and greenhouse gases. So my work involves a lot of chemical transport modeling, specialize in the use of remote sensing data to evaluate uncertainties in emissions, as well as the distributions of concentrations, and have, in particular relevance to this committee, looked a lot at the source attribution of deposition of SOx and reactive nitrogen.
Thank you. Next up is Robert Hilworth. Not seeing Robert. We'll move on to Donna Kensky.
Hi, everybody. I'm Donna Kensky. formerly of LADCO, a consortium of Midwest states working on air pollution issues in our member states. I am retired, happily retired. While I was at LADCO, I was a data analyst, working on receptor modeling and trends and some GIS work, but mostly analyzing air monitoring data. And I am now an independent consultant to CASAC and a few other people as well. Thank you.
Thank you, Donna. William McDowell.
Yes, good morning, everyone. Bill McDowell at the University of New Hampshire, currently as a research professor, recently retired as a teaching professor. I've done a lot of work on the connections between land and water over the last decades, and especially interested in the ecosystem function and the role in global to continental scale nutrient elemental budgets of small streams. So focus on small streams and how they reflect what's going on in the watersheds, and did also serve in the last case.
Thank you. Next is Hans Pearl.
Hi there. This is Hans. I'm with the University of North Carolina, the Institute of Marine Sciences here in Morehead City. Great to see a lot of familiar faces, by the way. And my interests are in impacts of nutrient loading on water quality issues, particularly phytoplankton, and have a strong interest in nitrogen depositional issues in estuarine and coastal ecosystems. And I think I overlap quite a bit with some of the other members as well. So we'll have a lot to talk about.
Great. Thank you. Richard Poirot.
Hi, I'm Rich Perot. This must be an old issue because so many of us are retired. I'm one of those. I retired at the end of 2015. I was the chief of air quality and climate planning for the state of Vermont. I was a former member of the CASAC statutory committee, and I think this is my 10th or 11th CASAC NOx review panel, depending on how many of the committees that got fired that we count.
All right. Thank you. A little another historical perspective. Next up is Alexandra Panek-Gonzalez.
Good morning, everyone. I'm an associate professor in the Department of City and Metropolitan Planning with a joint appointment at the Natural History Museum of Utah at the University of Utah. And my interests are in interactions between air pollution and ecosystems, with a more recent focus on particulate matter deposition to urban trees and forests. Thank you so much.
Thank you. Stephen Schwartz.
Good morning. I'm Stephen Schwartz. Also have served on previous incarnations of this panel, and happy to be back. I'm senior scientist emeritus at Brookhaven National Laboratory on Long Island, New York, also adjunct professor at Stony Brook University, which is nearby. My research interests have covered a lot of the territory that is in the purview of this committee, from acid deposition, atmospheric chemistry of the precursors of atmospheric deposition, sulfur and nitrogen oxides, evolving into the role of atmospheric aerosols on as climate forcing agents by their enhancement of planetary albedo and by their influence on clouds and precipitation. So that's sort of my technical background, and I'm looking forward to participating in this committee. Thank you.
Thank you. And last but not least, Kathleen Weathers.
Morning, everyone. I'm Kathleen Weathers. I'm at the Carey Institute, where I'm a senior scientist. I study air-land water interactions. I'm interested in biogeochemistry at that interface, and I've worked on everything from atmospheric deposition to effects on terrestrial and aquatic systems. I also have served on the CASAC in the past and this panel, and I'm very happy to be back.
Thank you. All right, so now we're going to move to the EPA presentation. Before I invite them to introduce themselves, I wanted to ask panel members to use the raise hand function if you have a question or a comment that you wish to make at any time during the presentation. I'm sure EPA will pause also and check in with us to see if we have questions, but if there's anything that you want to ask about, feel free to raise your hand. So now I invite EPA to introduce yourselves and to proceed with the briefing.
Okay, thank you very much, Leanne. Hello, everyone. I'm Erica Sasser, and I am the Director of the Health and Environmental Impacts Division. So my division is responsible for the policy assessment, and we work really closely with our colleagues in the Office of Research and Development throughout the NAAQS review process. It's a very large team for this review, and you're going to meet many of them. I'm going to let them introduce themselves as they begin to speak. We are in a conference room together, but the setup is not ideal for passing the computer around the table. So I'm just going to postpone that and start the presentation, and then as other folks come on, we will be sharing the presentation. We will have them introduce themselves at that time. Before I start, let me say, first of all, that we are extremely grateful to all of you for the time commitment that we know this entails. This is a big review. It's been going on already for a number of years. And we want to thank you for your service, both for those of you who were on the panel previously and contributed to the review of the integrated science assessment, as well as those who are now here to help us with the policy assessment. We appreciate your time. We appreciate the effort that it takes to understand these complex scientific issues, and we really look forward to hearing your expertise and your advice to us on the review. We also want to say thank you for your patience on a number of fronts. We know that this review has been relatively slower moving than is typical, and that is a reflection of the complexity of the science, which we will begin talking about in more depth in a few minutes. We also thank you for your patience in waiting for the release of the draft policy assessment. That document we had hoped to have in advance of the meeting. We are almost ready. We are working on some last minute formatting issues, and we will be sending that to you tomorrow. So you will have the full document tomorrow. We have today a pretty extensive presentation, and we hope that as we go through the presentation, you will ask questions. This is a chance for us to help orient you towards the document that you will be getting tomorrow, and also to identify some of the key decisions that we have made as we have grappled with how to translate the science into policy. And I'm going to talk more about that as we go through the slides here. This review, I've been at EPA for almost 20 years working in the NAAQS program, and I will say that this is the most complicated review we have undertaken. So there are a number of reasons for that. We've got multiple pollutants. We've got some pretty complicated relationships between ambient air concentrations and deposition levels and the array of effects that are associated with that. We'll spend a lot of time talking about those relationships and how we can sort them out for purposes of making policy decisions. We also, in many cases, lacked data that we would have liked to have had to do more quantitative assessment of, that relates ambient air concentrations to effects on the ground. And so in a number of instances, we will discuss approaches that we took and approaches that we tried and were unable to to bring to fruition. So we have a lot of work that has gone into the final document, the final draft that you're going to see tomorrow. So I think what I'd like to say is we're bringing you our best thinking up to this point, and we look forward to your reactions to that and your advice to us with regard to how this informs the decisions that we make on these standards. We are reviewing 3 separate sets of standards here. We're reviewing the oxides of nitrogen, the oxides of sulfur, and the particulate matter secondary standards. The complex chemistry underneath this system makes this particularly challenging. So let me go now to the next slide and introduce you at a high level to the team. As you can see, there are a lot of folks on this slide. All of them have played a critical role in the document that you will get tomorrow, as well as in the integrated science assessment. You will be hearing from a lot of these experts, and they will introduce themselves as they go. Within my division, there's a whole host of folks there. You'll hear from Karen Wesson today, Ginger Tennant, Deirdre Murphy, Pat Dolwick, and others. You will hear also potentially from some of our air quality staff and from folks in the Office of Research and Development, as appropriate given your questions today. And there's a little chart there that you can refer to if you're confused, which we understand because it's a big organization here and it can be very confusing to figure out who sits where. This slide is designed to help orient you towards the speakers and so on. So I encourage you to refer to this if you need it. Okay, let's move to the next slide, please. We wanted to start out by orienting you towards our timeline. This review began in 2014 and has progressed with, through a number of milestones already, including the integrated science assessment, which was finalized in 2020. And last fall, we were under under some litigation to try to complete the review because we had missed our 5-year deadline. So we did enter a consent decree, and that schedule becomes important now as we move forward. So the dates here really reflect both today's meeting, as you see, and the draft PA being released tomorrow, as well as the upcoming CASAC meetings that have already been scheduled for you to deliberate on the PA and then to discuss your draft letter. But leading towards a proposal date of next February, which is really extremely soon. And we're working very hard to meet that date. So you'll see that there are both proposal and final decision signature dates under the consent decree that we are working to meet. Next slide, please. So today what we want to do, as I said, is orient you towards the document that you're going to get tomorrow. We're going to take you on a journey that starts with some of the overarching considerations in the review and the challenges that we faced. And we will focus on information about current levels of air quality, the trends in emissions and deposition, what we know about wet and dry deposition in different environments, and then how we relate those estimates to ecological effects. So the big challenge in this review, which Karen's going to talk more about in a minute, is really taking that journey from emissions all the way through deposition, through ambient concentrations, to deposition, to effects, and back again. Because at the end of the day, we have to set standards that are based on ambient air concentrations. So the main effects that we are focused on are outlined here. They are direct effects on vegetation, aquatic impacts from deposition, and terrestrial impacts from deposition. And we're going to talk about each of those sections in some depth in today's presentation. Then we go back to the question of how we relate air quality concentrations to deposition and what that means for the standards and the staff conclusions on whether it's appropriate to retain or revise the standards for the pollutants under review. And we will have lots of time for questions and answers. We would like to encourage you as we go through the presentation, if you have questions, we're going to stop at the end of each section to see if there are questions. But if you have a question as we're speaking, please use your raise hand function, and we will do our best to address them in near real time so that we can make sure that we're all kind of moving together through this presentation. Okay, next slide, please. All right, at a very high level, I want to stress a couple of points before we get into the science for this review. The Clean Air Act, there are two sections of the Clean Air Act that govern the National Ambient Air Quality Standards. Section 108 is where the Clean Air Act describes the scientific basis that the agency must establish for the review. And these are known as the criteria. So the criteria are laid out in the Integrated Science Assessment. That document was finalized in 2020. Many of you were, I think most of you, in fact, were part of the review of that document. And that document is designed to be fairly encompassing. So it's designed to capture the latest scientific knowledge that is useful in indicating the kind and extent of all identifiable effects on, in this case, public welfare, which may be expected from the presence of the pollutants in the ambient air. So it's pretty comprehensive, and we had quite an array of different endpoints that were evaluated in the ISA. From there, we move into the policy portion of the review, where we actually decide what standards must be set. And the Clean Air Act says that the secondary standards should specify a level of air quality based on the criteria, based on the ISA, that is requisite to protect the public welfare from any known or anticipated adverse effects associated with the presence of the pollutant in ambient air. So I want to point out a couple of things here. First of all, standards are defined in terms of air quality. And this is a challenge in this review because we are not setting deposition-based standards, we are setting air quality standards. Okay, very important point. Second, the word requisite is very important. Requisite means sufficient, but not more stringent than necessary. So in exercising his judgment, ultimately, the administrator must decide that a standard is necessary to protect the public welfare without being overly protective, for example, in the face of significant uncertainty. So the Clean Air Act clearly, and this has been litigated in a number of different cases, the Clean Air Act does not require us to eliminate all risk. And in fact, the courts have said zero risk standards are neither possible nor required. But this leaves us with a lot of judgment about how to translate the complex effects into standards that are appropriately protective. Welfare effects include, under the definition in the Clean Air Act, quite an array of different effects. Not all of them are under review here, although a number of these are at the center of this review: effects on soils, water, vegetation, wildlife, etc. Another thing that is important to point out is that an adverse impact at the ecosystem scale or at the individual plant scale is not necessarily the same thing as an adverse effect on public welfare. So the charge under the Clean Air Act to the administrator is to determine which effects rise to the level of being adverse to public welfare at the national level. And so again, this review has many, many, many types of effects. We're going to talk about those in depth. We're going to look at different types of effects in different ecosystems and on different types of organisms. At the end of the day, though, we must translate that back into standards that are requisite to protect the public welfare from an overall social standpoint. The courts have also provided some additional guidance on the judgments that the administrator makes in this process. First of all, saying that EPA is required to engage in reasoned decision-making to translate scientific evidence into standards. So that has to do with making reasonable interpretations of the evidence and the uncertainties in making decisions about the standards. Also, the courts have said that we may not consider cost in setting the standards. So in other words, the fact that a standard may be difficult to implement or may be expensive is irrelevant to the decisions on the standards. We do consider cost when we think about the appropriate strategies to implement a standard, but that is not part of the phase that we are working on now. That comes later after the standards have been set and or revised. Okay, next slide, please. Okay, this is the last general slide, but I think it's worth just walking through for those of you who have not been part of a review before, or you may have seen this slide, but it's been a while since we walked through it. So let me just do that again. The role of the policy assessment in the NAAQS process is to help bridge the gap between the integrated science assessment and all the quantitative information that's available or that we generate, and the decisions that are required of the EPA administrator. So at its heart, the policy assessment asks the question, does the evidence and quantitative information call into question the adequacy of the existing standards? In this case, we're reviewing multiple standards, so we're asking that question with regard to the standards for NOx, the standards for SOx, and the standards for PM. So we look at all of the inputs. We look at scientific evidence in the ISA, the quantitative risk and exposure information, your advice, and ultimately, and public input, of course, at multiple stages. And then we answer the question, should we consider revising the existing standards or should we consider retaining them? And if the answer to the question of revision, if we can say that we should consider revising, then the role of the policy assessment is to lay out the alternative standards that may be supported by the evidence. And that includes all the elements of the standard. So we're looking not just at the standard level, but also the indicator, the averaging time, the form, and the level itself. And we'll talk more about those as we get into the review, because in this case, we are concluding that there might be reason to think about adjusting the averaging times, forms, and levels of some standards. Okay, unless there are questions about the general slides, I'm going to now I'm going to literally pass the computer to Karen Wesson, who is going to start in on the specifics of the review.
Erica, may I ask you a question?
Of course. Go ahead, Praveen, and I see Stephen.
Oh yeah, thank you. I don't see raise hand here, so I'm just going to raise my hand in my little picture. But the quick thing, previous assessments, the way I got it, you had the ISA draft, second draft, final, and so on. Then we used to have what you used to call REA, risk exposure assessment, as a separate standalone process, and then get into policy assessment. I'm looking at this slide, the last one. I'm assuming what we see tomorrow also includes the quantitative exposure risk assessment as a part of policy assessment and not a standalone risk exposure assessment. Is that correct interpretation?
Yes, that is correct. And I should have mentioned that. In this case, all of the quantitative analyses are embedded in the policy assessment. So as we go through discussion of each type of effect, we will be presenting you the quantitative information that's relevant to that endpoint. And in some cases, there are some lengthy appendices that also provide a lot of further information and analysis that we conducted, but it was too lengthy to embed in the document. So you will see all of it in one package.
And if I may ask one more time, you mentioned earlier consent decree. So September last year, I'm assuming effect of that is simply on timing and what EPA needs to do by a certain time this year, next year?
Yes, that's right. It requires us to complete the review by the dates I mentioned earlier, which the proposal next February and the final rule in December of 2024.
And consent decree does not include issues of scientific questions or policy questions, just
No,
timing.
It's
Okay.
just a timing issue.
Thank you.
Thank you. Looks like Stephen Schwartz has his hand up too.
Yes, thank you. I come at this in some sense from the perspective of an atmospheric chemist. And if I understand it correctly, any standards that are to be set have to do with concentrations of materials in air. Is that accurate?
Yes.
Okay, so I see the challenge, I think, at least to the standard settings side of things, is let's suppose that there's an effect on some sort of ecosystem as a consequence of deposition. But the standard has to be set for concentration. So therefore, that requires a link between concentration, not necessarily at the surface, it could be throughout the mixed layer, throughout the atmosphere vertically, and deposition. And that's a challenge. That's a big scientific challenge. Do I understand that correctly?
You do, and we're going to orient you today to the approach that we took in making that translation. So that's one of the fundamental questions in this review is, have we done that correctly? And can we then interpret what level of an ambient standard is necessary to protect against the level of deposition that we think is required to protect the public welfare? So in essence, it is a giant translational step, and we're going to walk you through how we approached it.
Okay, I agree with you. It is a giant translational step. It's a giant scientific issue as well. And I see that as a challenge to the standard setting process. There's another challenge, which I don't think is within the purview of this activity, which is translating that ambient air concentration that we have somehow just set to how to achieve it, which is through controls of emissions somewhere, sometimes someplace, to achieve that. And am I correct in understanding that chain of reasoning that goes from emissions to air quality standard is not in the purview of this activity?
That's exactly right. Once the standards are set, the states themselves states who have non-attainment areas would have to go figure out which emissions controls they wish to adopt to meet the standards. So that is not part of the review. The implementation considerations are not at all part of what we're going to be talking about.
Okay, that does indeed help clarify matters for me. Thank you on that. As you were just speaking and you said the states have to do this, it's also a challenge in the event, which is very likely the case, of interstate transport of material. How does one state, such as New York, control achieve its attainment by controlling emissions in, say, Indiana? But that's again not within the purview of this committee, if I'm correct in my understanding.
You are correct. And there is a separate section of the Clean Air Act that is devoted just to that question of interstate transport. So there are mechanisms under the act by which that can be addressed, but it's not part of the CASAC's job in setting the standards.
Okay, but just, thank you. But just to confirm, the relationship between air quality as measured in concentrations of NOx, SOx, and PM to deposition is certainly within the purview of this activity.
Yes.
Okay, thank you so much.
Sure. Thank you for the questions.
Thank you. Jim, you had your hand up?
Yeah, just a follow up. Stephen had mentioned ambient air and concentrations throughout the atmosphere. Just to be clear, I think the standards are set at the surface. Is that defined as ambient air, or is it actually throughout the atmosphere? Could you clarify that?
So the standards are measured at ground level, right? So the ambient concentrations that are being measured by the monitors that ultimately would determine attainment or non-attainment are at ground level. However, I do think that it's a good question, because in this case, as we look at deposition, of course, what is emitted in one place moves elsewhere. And so there is this translational puzzle that we have to solve to figure out what ground level concentration measured at a monitor in place X effectively controls against harmful deposition in other locations. And again, we're going to walk you through how we approached that. And we're going to relate it back to concentrations that would be measured at monitors at ground level.
Yeah, thank you.
Okay, now
Go ahead.
I'm handing you over to Karen. Okay.
Hey, good morning. So my name is Karen Wesson. I am the group leader of the Ambient Standards Group. So my group leads the drafting of this policy assessment document. Thank you for all the good questions this morning. I'm really hoping that we can bring some clarity to some of those in a little bit more detail in some of the slides to follow. So I'm just going to start with a little bit more background, getting a little bit more detailed. So as you can see, if we've not already expressed it, this review is complicated. So we have 3 different standards that we're looking at, and I'm just going to walk you through a little bit through these standards. So first, starting with the NAAQS for oxides of sulfur, we have a standard that's set as an SO2 indicator. That standard is set to reduce peak concentrations. It's set based on a 3-hour daily max at a level of 0.5 ppm, and that is not to be exceeded more than once per year. With respect to particulate matter or PM, we have an indicator of PM 2.5. We have 2 standards, secondary standards. One is an annual standard. One focuses on controlling peak concentrations. The annual standard is set at a level of 15 micrograms per meter cubed, averaged over 3 years. We also have the 24-hour standard, which is set at a level of 35 micrograms per meter cubed. It's set with the form of a 98th percentile, and that is averaged over 3 years. We also have a PM10 indicator standard. That is a 24-hour standard. It's set at a level of 150 micrograms per meter cubed, and that's not to be exceeded more than once per year over 3 years. And then last, for oxides of nitrogen, we have a standard that's set with the indicator of NO2. It is an annual mean standard, and the level is set at 53 ppb. So moving to the next slide, the standards we just went over, generally they were established based on preventing direct effects of the pollutants in the ambient air. So for SO2 and NO2, those standards historically focused on protecting against direct phototoxic effects on vegetation. For PM, those standards have historically focused on protecting against visibility, climate, and materials damage effects. For those of you who are familiar with the 2020 PM NAAQS, which is currently undergoing reconsideration, you will note that that review tackles and looks at the protection provided by the PM secondary standards against these effects there. And so thus in this review, we are instead looking at the effects to ecological systems from PM. So the current review focuses on the adequacy of those standards I just went over. It looks at the protection provided against both direct effects on vegetation as well as deposition-related ecological effects. So it's looking at both of those sets of effects. I think it's worth mentioning that unlike the 2012 review, this review includes evaluation of the PM standards. As with the past review, it focused on oxides of nitrogen and sulfur. Here we include PM, and PM was brought in to more holistically assess and evaluate the impact of all nitrogen compounds on the ecological systems. In this draft, we consider the available scientific information as assessed in the ISA, which was made final in 2020. In addition, we also look at the policy relevant quantitative air quality exposure and risk analysis, which, as Erica mentioned, are included in the policy assessment document. So moving to the next slide, some background. I know many of you were involved in the 2012 review, but just touching on some of that background for everyone's sake. That review, while it included an assessment of direct effects like this review does, it focused on consideration mostly of deposition-related impacts. The administrator concluded as part of that review that the existing standards for oxides of nitrogen and sulfur did not provide adequate protection for ecosystem effects of deposition, and pointed to the levels of deposition at that time, which were focused on deposition of nitrogen and sulfur in the early 2000s. As many of you know, the REA and PA for the review explored an option for setting a standard based on a newly articulated aquatic acidification index, or the AAI. The AAI-based standard focused on looking at a minimum ANC level that should be maintained in different areas. It looked at concentrations of SOx and NOx specific to certain ecoregions. It looked at incorporating influence variables across the US, and more particularly, it looked at inclusion of modeled-based inputs into the setting of that standard, into the specification of that standard, including, for example, air quality information coming from the CMAQ model, and inclusion from that model of estimations, for example, of what they called transfer ratios. So that review concluded in 2012. The administrator concluded that uncertainties and limitations in the available data from which such a standard would be articulated were too significant to support establishment of a new AAI-based standard that could be concluded to provide the requisite protection for such effects. So moving to the next slide. So in this review, we recognize the complexity of such a review, both the scientific complexity as well as the policy relevant complexity of the review. Our aim is to find an appropriate balance between the potential, between the precision of the potential solutions and the confidence that such a solution will be successful in achieving the air quality and deposition goals that are most appropriate. And looking at the considerations and challenges that we have in this review, first, as we've noted, the NAAQS are set based as national standards that are measured as air quality concentrations at EPA-approved monitors. And at those monitors, there are federal reference methods or federal equivalent methods that are established that maintain how that monitor measures that indicator. This review is unique in many ways, but it is not unique in considering control of deposition-related effects via an air quality standard. We do this for multiple other NAAQS. For example, in the lead NAAQS, we do look at deposition effects that are related to emissions of lead and how the air quality standard for lead controls and provides protection against those types of effects. And then also another example I'll provide is the PM standard, where we are looking at deposition-related effects on materials damage, again, with an air quality standard for PM. Some of the different and unusual challenges in this review, there are several, and I just wanted to list out here some. First, deposition levels can vary across the US due to a variety of factors, including variability in emissions, frequency of precipitation, meteorological factors relevant to dry deposition, and those include wind speeds and humidity, atmospheric stability, temperature, multiple factors that influence that variability. Second, the degree of ecological effect does not vary with the level of deposition everywhere in the same way. So we know in some areas there are ecosystems that are more sensitive, while where in other areas there are ecosystems that are less sensitive. And third, worth mentioning is that there are many decades of historical deposition that are still affecting ecosystems today. and teasing out what is the effect from historical deposition versus what is the effect of current air quality concentrations is a science and a policy challenge. And then lastly, in many cases, the impact of deposition and how one views that with respect to policy science questions regarding adversity, and as well as regarding the level of protection needed against public welfare is complex. And it is not always straightforward in all cases. I think a great example is nitrogen deposition in cases where you can get impacts that both promote growth as well as have growth decline results. And then lastly, for this side, it's as we've noted before, decisions on the approach to take in achieving the desired air quality and the public welfare protection. They are largely public welfare judgments. And as such, they do fall within the scope of the administrator's judgment. And let me stop there. I'm happy to take questions if there are any. The next set of slides will start getting into air quality information and trends and associations just a little in more detail. But let me stop and see if there are any questions. Okay, if not, let me go ahead and let's jump into one second. Oops.
Hello, can everybody hear me?
Yeah, we can hear you.
Thanks. I'm Pat Dolwick. I'm the Science Advisor in Health and Environmental Impacts Division here within Office of Air and Radiation and EPA. I'm going to walk through sort of the highlights of the air quality chapter of the policy assessment. I think as many of you are familiar, the air quality chapter is sort of a foundational element for all the effects evidence that comes, sort of characterize what we know about atmospheric chemistry, sources of the pollutants under this particular NAAQS review, how they're changing with time, and then in turn, what concentrations look like. First off, how concentrations are monitored, what concentrations look like, how they're changing over time, and we're also going to talk about how deposition is calculated. Yes, Stephen.
Yeah, sorry to interrupt. I just would like to confirm that in dealing with the secondary air quality standards, we are not considering matters of impairment of health as a consequence of air pollutants. Is that correct?
That's correct. They're covered under separate reviews.
Okay, thank you. I just really wanted to confirm that. Thank you.
Thank you for the question. Next slide, please. Okay, just a simple schematic to start us off, and this has come up under already a couple of times this morning under some of the challenges that we're facing with this particular review. Obviously we're dealing with 3 separate criteria pollutants: oxides of sulfur, oxides of nitrogen, and particulate matter. And the chemical components of each of these pollutant categories they're multifaceted. So for oxides of sulfur, the primary one is sulfur dioxide, SO2, but there are others. The indicator species is SO2. Oxides of nitrogen, we have NO and NO2, which comprise NOx, but many other oxidized nitrogen compounds, including nitric acid and nitrous acid and others. Then within PM, we have a number of different PM components, including some that are unrelated to nitrogen and sulfur deposition, like elemental carbon, organic carbon, crustal species, but some that are related to sulfur and nitrogen deposition, which include ammonium, but also sulfate and nitrate, which then, collectively or respectively can be part of either oxides of sulfur for sulfate or oxides of nitrogen for nitrate. So
if I may interrupt you here.
Yes, Praveen, please.
Oh, thank you. I just want to be clear, the history of this. What's missing here is ammonia, not just ammonium, but the gas itself. And we've gone through this discussion earlier, the reduced nitrogen, oxidized nitrogen, NOx versus NH3. I think here you may want to be very clear that within PM or a different circle, ammonium, because ammonia leads to ammonium. So I guess it's kind of explicitly missing, and I think it should be here.
Thank you, Praveen. We will consider that for the schematic. I assure you that the policy assessment itself discusses ammonia and reduced nitrogen species in some detail. But I appreciate that comment on the schematic itself.
Oh, thank you.
If we can move to the next slide. Oh, yeah, I guess the last thing I'd close out that slide with is just that, a point that Karen made as well, which is, so obviously this puts the sort of a spotlight on the importance of understanding that sort of pathway from emissions through atmospheric chemistry, through transport, eventually into deposition, and then on to effects. There's a wide variation in how each of these individual pollutant compounds deposit to the Earth's surface. And so that's something that the policy assessment tries to explain, leveraging the ISA as fully as possible. Okay. Sorry, Aaron, next slide, please. Okay, talk a little bit about the sources of emissions. So starting with oxides of sulfur, mostly this occurs through combustion, and the primary oxide of sulfur in the atmosphere is SO2, sulfur dioxide. I think as many know, sulfur dioxide can be converted to sulfate particles, either through oxidation in the gas phase process with sulfuric acid or in an aqueous phase process as well. Conversion rates can range from about 0.5% per hour to something much higher than that. The dry deposition is the primary or the main removal process for SO2, whereas sulfate tends to be more efficiently removed within wet deposition. I don't know how visible, hopefully everybody has 27-inch monitors, so I don't know how visible these pie charts will be, but I'll walk through them. For SO2, and all these plots are based on the most recent national emissions inventory data, the 2020 NEI, which was just released, I think, within the last couple of months. For SO2, the primary sources are coal combustion. Even in 2020, despite a lot of the decreases, about half of the SO2 emissions within the US are still from stationary fuel combustion of coal. But other important categories include industrial processes, the gray slice of the pie there, which is 27%, and fires, which combining agricultural, prescribed, and wildfires is about 12% of the SO2 inventory within the NEI. For NOx, again, this is NO plus NO2, we have a more balanced split of the sources of emissions. Mobile sources, whether on-road or highway vehicles or non-road mobile sector, comprises about 45% of the inventory collectively. And then the next most important sector is sort of the stationary point source component, be that, from the power sector through stationary fuel combustion or from other industrial processes. Those two combined are about 37%. About 12% of the NOx within the NEI comes from biogenics, and there's a smaller contribution from fire. And then finally, yes, Praveen, sorry.
Yeah, sorry to interrupt, but I just want to be clear, and this is the history here. Thinking about SOx, thinking about NOx, you got to also think about ammonia the same way. Here, the last one, you simply said particulate matter. I would say, the third bullet should be ammonia. And you have a pie chart, of course, on the right of ammonia emissions, not PM emissions. So I just think ammonia clarifies your thinking if you think of ammonia as ammonia, not as something else.
Yeah, I appreciate the emphasis on the reduced nitrogen, and again, assure you that that's a major component of the policy assessment itself. As the slide here talks about how reduced nitrogen species, including ammonia, for example, ammonia can contribute to particles. I think we framed it as oxides of sulfur, oxides of nitrogen, and PM, because those are the criteria pollutants that we're reviewing. But obviously, ammonia is a significant contributor to what we see in terms of particulate matter.
And again, to be clear, I don't want to be nitpicking, but you said reduced nitrogen species can also contribute. I would simply say contribute. It's not a question of can or cannot. They just do.
That's fair. That's factual.
Yeah, let me weigh in for a second and just remind all of us that our goal today is to get briefed from EPA on what they did, and so we should focus most of our dialogue with EPA on clarifying questions to make sure we understand. We will have 2 full days to deliberate in June, and so we should prioritize deliberating on a number of aspects for the June meeting.
Thank you, and appreciate the questions and the clarification there. The in terms of the ammonia emissions in the 2020 NEI, I think you can see that almost 80% of the emissions are coming from agriculturally based sources, whether that's livestock waste or fertilizer application, with smaller contributions from other sectors. Next slide, please. Okay, we talked about the sort of sectoral contributions to each of those 3 pollutants, SO2, NOx, and ammonia. Now we just wanted to sort of briefly describe the spatial pattern of those emissions. So again, this is data based on the 2020 NEI. We're looking at emission density plots here. We've looked at each of the 3 pollutants, sort of categorized the emissions density in 5 bins, where the darkest blues are the counties that have the highest emissions densities in terms of tons per year per square mile. And then the lighter colors, obviously less. For SO2, I think this is probably already pretty familiar to folks. The Ohio River Valley has many coal-fired power plants along its shores, and despite the copious emission reductions that have occurred within the past 2 decades, which we'll show in subsequent slides, still tend to be one geographic location that is still very high in SO2, but it's not the only one. You can see other source-specific counties in Texas and other parts of the U.S. Moving down from the upper right to the lower right, let's look at the emission density patterns for NOx. It's a little more well distributed, at least across the eastern United States, although certainly you see that the highest emission densities are in the major metropolitan areas. And then finally, ammonia. I think to no one's great surprise, the greatest density of ammonia emissions are in those areas with strong agricultural production. So areas in the upper Midwest, Iowa, southern Minnesota, into the Corn Belt of Illinois, Indiana, but also other specific locations, for instance, Duplin County in eastern North Carolina, where there's substantial amount of hog farming, and then also parts of the Central Valley of California. Next slide. Okay, we advertised this going forward or in the past, but another sort of key challenge of this particular review is that, especially as it relates to the previous review, is that the review is taking place in a time of major transition in the sort of air quality across the United States. And emissions trends in SO2 and NOx have trended sharply downward. We're going back to 2002 in this particular plot. And so when we look at SO2, we can see that, again, based on National Emissions Inventory estimates, that the SO2 totals have decreased by 87% over the last 20 years or over that 20-year period. This is due to rules like the NOx SIP call, the Clean Air Act, or excuse me, the Clean Air Interstate Rule, a number of different mobile-focused rules, as well as technological improvements. So For SO2, most of the reduction has come in the power sector, 91% over that 20-year period, and from the transportation sector, where we've seen a 96% reduction in emissions, SO2 emissions since 2002. NOx over that same period has also been declining, although not quite as much. So 68% reduction over that 20-year period, again, driven primarily by highway vehicles and the power sector. We don't have the plot shown here in this sort of subset of highlight slides that we're sharing today, but it's certainly part of the PA. We have plots looking at ammonia emissions over that same time period. They are relatively flat or perhaps have slightly increased in that sort of 0 to 10% range over the past 20 years. Next slide, please. Okay, let's transition to, how do we build our understanding of the air quality concentrations for each of these species, or, the air quality monitoring network that collects this information. Over the US, we have a relatively robust, extensive, and high quality air quality monitoring network. I've just shown here a sample of, for both SO2 and PM 2.5 mass, where the monitors are located, and what network they belong to. We have, as Karen alluded to, these networks are primarily federal reference method based or federal equivalence method based. For SO2 across the country, we have about 500 monitors. NO2 is essentially a similar number. For PM mass, we're over 1,000 monitors across the US, with about 300 monitors going beyond PM mass and providing, some measure of what the component species are within that mass. Some of the terms, and these are described in more detail within the PA itself. Networks I suspect many of you are familiar with are SLAMs, the NCOR, National Multi-Pollutant Monitoring Network. One thing that's new since the last review is the Near Road Network. Within the past 7 years or so, we've built a pretty robust community set of monitors that are located very close to major roadways. And then there's an additional set, whereas those are the ones that are most NAAQS relevant. We also have a number of different networks that we leverage for PM component monitoring, including the Chemical Speciations Network, Improved CASNet, and Ammonia Monitoring Network. I see two questions, or two hands raised.
Go ahead, Judy.
Yeah, I was wondering that, would you consider the PAMS network, the Photochemical Assessment Monitoring Network?
Yeah, any measurements from those any measurements from PAMS are certainly informative to sort of building our air quality characterization. Those, as you know, are mostly focused on ozone and ozone precursors. And so, to the extent that that sort of information can inform our understanding, certainly they'd be considered. But PAMS is not a big part of what we're doing here, looking at the nitrogen and sulfur related compounds. It could be that I'm not so intimately familiar with what the PAMS monitors measure. There may be a species or two that could be beneficial, and that would certainly be useful advice from the CASAC.
Then they have an OI. Also, that ammonia monitoring network, the AMON network, is only about 90 some sites. They are part of the NADP. Do you consider everything of the National Atmospheric Deposition Program?
We do, and we kind of broke up this set of slides and also the discussion within the PA. First, talking about sort of the air quality concentration and the monitoring in that realm. And then in a later chapter of section 2 of the PA, we talk about deposition monitoring and how we estimate deposition. So that's coming.
Okay, thanks.
Yes.
Thanks. Kathleen, go ahead.
I'm just wondering whether somewhere down the line or in the report, you'll indicate what the time frame is for these monitoring networks. It occurs to me that some of them have just been instituted recently. Some of them may have been phased out. So it'll be important to know how long these networks have been in place and how long the data have been monitored.
Yeah, that's an excellent point. And I think that is embedded within the text of the PA. I think, one of the things, we provide more detail as to sort of the methodology itself, whether it's chemolucent, I'm not even going to try, based, or, what the technology of the monitoring is, the frequency of the monitoring. Some of these monitors collect hourly data. Some of them are filter based and may only collect data once every 3 days or once every 6 days. All that is described in the monitoring or in this section of the PA, as well as how long we have data back to. I guess the one thing I would say is I don't think, the CASNet network is in a period of transition now, and there's a lot of uncertainty around that. We haven't really spoken to that within the first draft PA.
And Judy, your hand's still up. That's leftover, I assume? Yeah, okay, go ahead, Pat. Thank you.
Thank you for those questions. Next slide, please, Aaron. Okay, and then just to provide some sort of grounding for air quality concentrations across the U.S. Again, only picked some samples looking here at secondary SO2 design values for the 2019 to 2021 period, secondary NO2 design values over that same period, and then the annual PM 2.5 design values. So starting with SO2, as Karen said, the current secondary standard is 500 ppb. This is a 3-hour standard, not to be exceeded more than once per year. The bins for this particular plot are somewhat subjective, but we capped it at 500 ppb, and no sites exceed that value. The current highest secondary SO2 design value is in Southeast Missouri and is 369 ppb. It's located near an industrial park, so that's one of the red areas. I'd also highlight that the higher values in Hawaii are likely due to volcanic emissions. They would certainly qualify for an exceptional event were they to ever be regulatorily relevant. So understand that the high values in Hawaii are a little different, have a little different source than the higher values across the 48 states. And then moving to NO2, the situation is the same. Again, a reminder, the current level of the NO2, which is a NAAQS based on an annual mean, is 53 ppb. We don't see values in the most recent design value period higher than 30. The highest is in Los Angeles. We see 8 sites that are in that range between 21 and 30 ppb, roughly half the standard. And then I think a lot of people are already pretty familiar with PM 2.5 design values. But as Karen listed in the NAAQS table before, recall that for the annual standard, the secondary level is 15. And so in this situation, we do see a handful of sites, 9, mostly in California, where we are, the data suggests that there are violations of the secondary PM 2.5 NAAQS. Pause for any questions there. Yeah, Jim.
Yeah, hi, Pat. Just for clarification, since the secondary SO2 is based on not to be exceeded, shouldn't the design value actually be the number of exceedances over 500? Is that not the design value? Is it really a value, or is it a number of exceedances?
That is the title here, as I started to introduce it, I recognized was unfortunate. I think what the title of the secondary SO2 design values, that should be replaced with a 3-year average of the second highest 3-hourly concentrations over the 2019 to 2021 period. You're right. The form of the standard, I mean, attainment, non-attainment would be based on whether or not you have shown the 2 exceedances over an individual year.
Okay, thank you.
That's a great clarification. Next slide, please. Okay, and then wanted to just sort of briefly sort of establish some foundation for what we know about various PM components. So again, let's start in the upper right and look at average sulfate concentrations. primarily from the chemical speciation network over a recent 3-year period. Again, we're looking at 2019 to 2021. I think is well understood, sulfates are primarily in Eastern US and Southern California, San Joaquin Valley type issue where, we'd see concentrations, exceeding 1 microgram per cubic meter of sulfate over large parts of the Eastern US. Although, in some places it's between 0.5 and 1 microgram per cubic meter, with lower values in the Intermountain West. Nitrate, the geographic patterns shift somewhat, as might be expected from what we saw from the ammonia emission density plots. And so nitrate values tend to be, again, high in the San Joaquin Valley and parts of Southern California, but also in, I guess what could generally be characterized as the upper Midwest, sort of, that range from parts of Pennsylvania through Ohio, Indiana, into Southern Minnesota and Iowa. Where nitrate concentrations, annual means can average, in excess of a microgram per cubic meter or higher. And then as we talked about earlier, again, one of the challenges with PM 2.5 is obviously you have other important components that may not be as relevant from a sulfur or nitrogen deposition perspective. So the plot in the lower left looks at, and I appreciate this is very likely very hard to read at this scale, but looks at sort of the fractions of not just sulfate and nitrate, but organic carbon, elemental carbon, crustal, and sea salt. So organic carbon, which is the sort of cyan, light blue color, obviously is highest in Northwest US and parts of the Southeast. Elemental carbon tends to be a very local urban issue, although not exclusively, can be source oriented as well. And then we get the most crustal emissions in the Southwest US, and you see that in the pie charts in places like New Mexico and Arizona. Next slide, please. Okay, air quality trends. Obviously, this brings, I think, joy to many people's hearts that have worked in the air quality community for decades. As would be expected, given the sharp drop in SO2 and NOx emissions over the past 20 to 40 years, we've also seen corresponding significant decreases in air quality concentrations. Again, the space sort of limits me to just a couple of examples. Not shown here is SO2, but we do have both figures and text in the PA that illustrates the fact that both short-term, sort of 3-hourly average type averaging times and longer-term SO2 metrics like annual means are sharply down over the past 20 years. NO2, we have a figure on this slide here in the upper right. We're looking at the distribution across all sites of annual mean NO2 concentrations on the y-axis. The box and whisker sort of shows how that overall distribution has declined from over a period from 1990 to 2021. Annual or median NO2 annual means back in the 1990s were on the order of about 25 ppb. Now you can see they're down to somewhere between 5 and 10 ppb. I'll just note the red line on this plot shows the number of NO2 sites within each individual distribution. And you can see that's been increasing over time. I'll acknowledge that there's been a slight flattening in the trend since roughly 2015. PM 2.5 in the lower right, we see similar decreases. Again, just now we're only going back to 2020 when most of the monitors, PM 2.5 monitoring network was put in place. Median values tended to be pretty close to the secondary standard, annual mean standard of 15, on the order of maybe 13 micrograms per cubic meter. And now you can see we're down in the range of, somewhere between 7 and 9 micrograms per cubic meter for the annual metric. And then finally, just on the lower left, looking at trends in annual mean sulfate, this time over a 16-year period from 2006 to 2021. And again, due to many of the major regulations that were put in place over the past 2 decades to regulate SOx and NOx emissions from the power sector, we're seeing significant decreases, statistically significant decreases on the rate of about 1/10 of a microgram per cubic meter per year, or maybe more intuitively, a microgram per cubic meter per decade over most of the eastern US. All right, next slide, please. Okay, as Judy teed us up for earlier, and as Erica sort of initiated the entire discussion, one of the challenges here then is how do we link everything we understand about air quality concentrations to total deposition, or to deposition, both total and sulfate and nitrate deposition. The policy assessment document itself has a number of figures, for example, of the NADP National Trends Network data, as well as the AMON network. But as a general term, in comparison to measurements of criteria pollutants, deposition measurements are relatively sparse across the US. And as such, most of our deposition analyses that feed into some of the risk effect analyses that will be described later are based on a combination of existing measurements, which are mostly wet deposition, and model simulations, mostly from US EPA's CMAQ model. And this is a field I think many of you are familiar with. It's the total deposition or TDEP data set. And while this is certainly an appropriate methodology, the PA highlights some of the measures of uncertainty that are introduced into the process by use of this hybrid approach. So yeah, the next slide has sort of a flow chart of a simple schematic of how TDEP works, but at its core, it's a hybrid approach that combines wet deposition from the National Trends Network, part of the NADP, which is 261 sites, a spatial field of precipitation data, which in and of itself is sort of a model measured mix called the PRISM data set, measured air quality concentrations from CASNet, which help inform, part of the bias correction that we try to do on the dry deposition side, which is about 101 sites, and then the dry deposition velocity data from the CMAQ model itself. This might make more sense in the next slide. So a simple schematic here, and doesn't capture all the detail. We have a more detailed schematic within the PA itself, but just sort of walking down the right side of that plot for dry deposition. It's a combination of inputs from CASNet concentration measurements, which in and of themselves are somewhat spatially limited, and CMAQ air concentration model results. Those are linked with the dry deposition velocity data from CMAQ, and we develop a bias-corrected dry deposition data set where the CASNet measurements are used to sort of ground check any potential biases within CMAQ itself. Those are corrected and then merged with some of the other dry deposition species, which are not measured, to come up with a TDEP dry deposition data set. And then on the left side of the plot, you can see as the flow of the process works from top to bottom. The starting point are your PRISM precipitation measurements, as well as the NADP wet deposition measurements. CMAQ is involved in this process as well, looking at the fractional contribution of ammonia to ammonium, and modifying TDEP wet deposition fields that way. I guess the primary takeaway in terms of orientation for today is recognition that the TDEP data set is subject to uncertainties associated with the idea that the measurement sites can be relatively far apart at times. And so capturing that variability between measurement locations is a source of uncertainty. Again, the dry deposition, very hard to measure. Accuracy of TDEP estimates are going to depend in large part on CMAQ model performance. And the policy assessment talks a little bit about our evaluation of that atmospheric model. The greatest uncertainties in TDEP tend to occur in those regions with substantial ammonia emissions, and attempting to account for the reduced nitrogen in those locations is a challenge. That was a very high level overview of kind of our foundational air quality chapter. I think I can stop here, take any questions, and then we'll move into the effects. Well, we'll move into the scope and approach and then the effects evidence sections.
Any additional questions for Pat?
Oh, I apologize. I gave up. I spit the bit. I have 2 more slides. And then Charles, I can address your question after that.
Okay.
Yeah, I apologize. Thanks to those in the room that flued me in. So spatial patterns of deposition. So we're kind of going to handle 2 things at once here. So sort of our understanding based on the TDEP estimates of deposition across the United States, first for sulfur, and the next slide will be for nitrogen, as well as the trends. So we'll look at both at the same time. So on the left, we have the 2000 to 2002 time period, units or kilograms of sulfur per hectare per year. And, at that time, it was not uncommon, especially in the Ohio Valley, to see, values in excess of about 15 kilograms of sulfur per hectare per year. We don't see anywhere close to that by, a more recent time period, 2017 to 2019. And then next slide is the same idea for nitrogen. The reductions in NOx NO2 emissions have been a little less than sulfate. And as we alluded to earlier, ammonia emissions might be increasing. So maybe it's not that unexpected to see not as dramatic of a shift. The PA itself has a really nice table that looks at the percent changes in each region of TDEP nitrogen deposition. Let me just say for sulfate, the regional decreases average between 38 and 87%. But for nitrogen, it sort of spans 0. There are some regions, particularly the north central US, where we are seeing increases in nitrogen deposition in the TDEP data on the order of about 11%, whereas there are other decreases. And I think you can see this from the illustration in this figure, like the Northeast US, where we've seen regional declines on the order of about 40%. Present day values across the US for nitrogen deposition range from about 3 to 10 kilograms of nitrogen per hectare per year. Okay, apologize for that, and glad to answer any questions. I think I saw Charles, then Davin, then Praveen, then Kathleen.
Okay, well, thank you very much for that presentation. It is really great news, and it's good to see that all together. So thank you. The question I had was on your partitioning of PM. And so I know that, you can't have anions and cations, but is there any way to sort of represent the ammonium contribution to PM? Have you looked into that? Could you address that?
The PA discusses sort of in concept what that looks like, and then we also do have plots of ammonium itself, just sort of nationally and how they've changed. So yeah, I think we've done what we could with the limited data sets to call out ammonium specifically. We're certainly interested in this committee's perspective of how fully we've described that and where there might be additional data sets that maybe we haven't tapped into that could provide a more comprehensive sort of clarification of the role of ammonia and ammonium in the overall PM and the role of ammonium in overall PM.
Thank you.
So I apologize. It's a little bit of a when you get the document in your hands tomorrow, we very much are interested in whether or not we've captured that appropriately.
Davin?
Thanks. Thanks, Pat. It was really nice to see this overview. And I had 2 quick questions. One is, if in the PA you also include an assessment of trends in ammonia concentrations. And second was on your diagram, sort of showing how the wet and dry deposition totals were inferred from a combination of measurements and modeling. On the wet side, is it that you have like total NHX from TDEP and that you're using CMAQ to say how much of that came from dissolved gas phase ammonia versus particulate ammonium? Is my understanding correct? Because it said from TDEP you have NH, that you have ammonium, but then also you're using CNAQ to get ammonium. So I wasn't quite clear about
I'll answer
that.
the first question, and then I'm going to phone a friend from our Air Quality Assessment Division, Colleen Boblitz, to address the second one. But we do not specifically have, unless I'm wrong, Deirdre, you may remember, I don't think we have trends in ammonia concentrations. We have trends in ammonia emissions, and we have trends in ammonium concentrations. But I think right now the PA is bereft of that sort of intermediate step. So, that might be a piece of feedback that we can take to improve the document. For the second question, I'm going to turn it over to Colleen.
Sorry. Okay, sorry. Thanks for your question, Davin. Okay, sorry. So my name is Colleen Boblitz. I'm a relatively new group member in the air quality modeling group here in the Office of Air Quality Planning and Standards. And so I helped contribute to the review for chapter 2. And so, one thing, so that's a great question and a good point of clarification. And so in the document, it's like in the caption, more or less, for the figures that show, the data that go into TDEP. And so TDEP is currently not bias corrected for ammonia in the same way that it is for the other compounds that contribute to those maps. And part of that is because, it's difficult, I think, as you know very well, ammonia, has bidirectional deposition. And so it's somewhat difficult to account for that in the same way in terms of the same methods that have been used for oxidized nitrogen. So right now that's not currently included in the TDEP maps. And so TDEP relies more heavily on the CMAQ fields for ammonia in that case. Thanks.
Thank you.
Sure.
Praveen, yeah.
Oh, thank you, Pat. I think you mean the last slide where you say uncertainties in nitrogen deposition estimates are largest in regions with substantial ammonia emissions. I think you mean they're the largest where there's a substantial uncertainty in ammonia emissions. Maybe not. That's the way I was thinking. Not just because the ammonia emissions are substantial, it's the substantial uncertainty in those emissions. I think.
Yeah, I think that's fair. I mean, maybe we skipped a step a little bit. The PA does talk in some detail about uncertainties associated with measuring ammonia and understanding ammonia emissions, particularly from the mobile sector, which I'm not an expert by any stretch of the imagination. But my understanding is that our collective understanding of ammonia emissions from mobile sources is maybe rapidly changing. So the idea is that there's more uncertainty in understanding ammonia emissions, and then that uncertainty then translates into the TDEP data sets. I think it's embedded in that statement.
Thank you.
And my question was right along the same lines as Praveen's, whether it was a lack of emissions estimates or it was about modeling the dry deposition that led to the uncertainties. So some clarification around what the uncertainties are would be helpful.
Yeah, and I think it's both. And I think we discussed both in the PA, though, whether the extent of the description is sufficiently explanatory is right along the lines of where we would love to get feedback. Okay, if that's all, and Leanne, if it's good with you, I think we'll move to the next section, and I'm going to turn it over to Dr. Deirdre Murphy.
Go ahead.
So my name is Deirdre Murphy. I'm scientist in Karen Wesson's ambient standards group. I've worked on a number of different NAAQS reviews, but this is my first foray into the world of the NOx review. And I'm just going to cover a couple of slides, really just take a few minutes to orient you on the overall approach that we've taken to evaluate the existing standards and policy, to evaluate the existing standards and potential alternatives in light of the current evidence and what it indicates regarding environmental exposures associated with welfare effects. So as Karen had mentioned, the 2020 ISA is our scientific foundation for addressing policy relevant questions on the welfare effects evidence and for identifying the welfare endpoints for which the quantitative information is most robust for supporting decision-making in the review. In drawing from this evidence base, the PA summarizes the welfare evidence in considering both levels of SOx, oxides of nitrogen, and PM in the air related to direct effects on vegetation and other species, as well as levels of sulfur and nitrogen deposition associated with various welfare effects. The quantitative analyses are performed for welfare endpoints for which the quantitative exposure risk information is considered the most robust, and for assessing the potential for occurrence of various effects at various levels of sulfur and nitrogen deposition. And to provide information over a long time period that, as has been mentioned, includes important reductions in emissions of sulfur and nitrogen and associated deposition. The assessment includes consideration of data spanning 20-year period with a focus on 5 individual time periods, 3-year time periods that are listed here from the 2001-2003 period up through 2018 to 2020 as the most recent one we were able to include. The welfare effects evidence in the quantitative analyses, including associated limitations and uncertainties, provided us with an ability to assess risk associated with varying levels of sulfur and nitrogen deposition in order to identify deposition levels of potential concern to inform consideration of a target level of protection for consideration of the NAAQS. As in the 2012 review, we have given primary emphasis to quantitative analyses of aquatic acidification as an area where the evidence is considered robust and approaches and tools well established. The air quality analyses are performed to investigate the relationships between sulfur and nitrogen deposition estimates and various air quality metrics for the oxides of sulfur and nitrogen and for PM. This is the piece of the puzzle which was emphasized a bit in the beginning, where there's a lot of complexity that we have to address in translating into the policy relevant world of a national ambient air quality standard rather than a deposition standard. And so we do these analyses to try and address the questions of what type of standard for which pollutants can most effectively limit deposition of these pollutants to the desired level. The PA then connects key findings for deposition-related ecosystem risk with relationships between air concentrations and deposition in evaluating the current standards and identifying appropriate array of potential alternative standards for the administrator to consider. So this is illustrated, this approach is illustrated on the next slide, or it's intended to illustrate the approach that we have taken in the PA in order to identify and evaluate policy options to address deposition-related effects. And while the document does address, as we've mentioned, the direct effects of the pollutants in ambient air, there's a lot of attention to this sticky wicket of deposition-related effects. The first major component of the approach is illustrated on the left side, where we weigh and evaluate the scientific evidence along with quantitative information and analyses in order to identify a range of deposition levels and key welfare effects of potential concern. The second major component is on the right-hand side, and this involved an analysis of air quality measurements and deposition estimates along with model estimated spatial relationships in order to characterize air quality relationships between nitrogen and sulfur deposition and pollutant concentration metrics. And then these are brought together for us to consider policy options regarding existing and potential alternative standards. As was mentioned earlier, it's quite a complicated task because it's taking a lot of evidence and information, which is quite highly technical, quite comprehensive, goes into lots of different alleyways, if you will, and we try and distill it up to something that is scientifically sound, but also and useful in a policy relevant way, and also clear and understandable. So we do welcome your attention to whether we've met those criteria. I can take questions, but it's just a couple of slides before I pass it on to Ginger to delve into some of the information with regard to welfare effects. Can you change the name? Okay, so we'll start with the next slide. So before I get started, I want to just say that there's a lot more information in the document than you're going to see in this presentation. And what I'm trying to do is to just kind of give you a sampling, sort of an overview of the context for what you're going to see in the document. But there, in the time that we have, there's no real way to go into the amount of detail that we have there. So that said, feel free to stop me if you have any questions. But we should have plenty of time in the CASAC meeting after you've seen the document and had a chance to wrestle with the kinds of analyses that we did to sort of opine more fully on the way that we chose to do the analyses and how we've chosen to present them. And we would certainly value your input into how clearly and how well we have addressed those issues. So first, like I said, we're just going to focus on the key welfare effects endpoints that we did highlight in the policy assessment. And as we've talked here, we talked about sort of two bins of effects. We have the direct effects on vegetation from SOx, nitrogen oxides, and PM. And then we have the deposition related effects, which of course are more complicated, relating to deposition of sulfur and nitrogen. And for that, we looked at both the aquatic and the terrestrial effects. So if you go to the next slide, please. Which is just to tell you that we're going to talk about the direct effects on vegetation. So we'll just move on to that slide. Okay, so, oh, I'm sorry, Praveen, I didn't see you. Did you have a question?
Well, I think I'm on Zoom. I'm trying to get back.
Oh. Okay. Anyway, so as in the last review, the current ISA continues to conclude that SO2, as well as oxides of nitrogen, including the suite of things that we consider there, the NO2, NO, PAN, nitric acid, and others, can cause injury to vegetation. And so what we tried to do is, with respect to SO2, we looked to see what kind of evidence we have, and we have controlled exposure studies that have shown visible foliar injury from SO2. And so we've looked more fully at those, and we also have recent studies that report effects on lichen. And so when we think about those things in the context of the levels of the current SO2 standards, we look to the ISA, where it's also concluded that there was no evidence of these kinds of acute foliar injuries below the level of the current SO2 standard. And so similarly, with respect to the oxides of nitrogen, we have studies that reported reduced photosynthesis, visible foliar injury, as well as growth effects in plants. And we looked at those studies to see what they could tell us about the range of impacts that might be expected under the current levels of the standard for these direct effects. And for that, we looked at the ISA, which noted that the effects that we're seeing for oxides of nitrogen in the literature have been reported at concentrations that were well above the current level of the standard. So next slide, please. Okay, so we also looked at PM and regard to PM on vegetation. And while the ISA found that there's the body of evidence sufficient to infer a likely causal relationship between the deposition of PM and a variety of effects on individual organisms and ecosystems, we note that most of that evidence was related to the components of PM, such as metals rather than the mass, and that there is limited evidence available for PM, and what there is available at very high levels, far above the level of the standard. So for PM, we focus mostly on the evidence that links PM and ecological effects relating to the deposition of nitrogen and sulfur. Okay, and so that's sort of the end of the discussion on the direct effects. Were there any questions on that?
Also, before I move on, I see that you have a couple more sections. I think we should take a break after questions, either on this section or the next section. I'll defer to you all at EPA when you want to, when you think it's a good stopping point. But it looks like Stephen Schwartz has his hand up first.
Yes, thank you. In especially looking at effects on vegetation, I see reference to sulfur and nitrogen, but my understanding is that in many instances it's deposition of total acidity rather than specific ions there, and I'm wondering whether that is considered somewhere in the report.
Yes, we'll talk about that more in the deposition related effects. It's a little challenging to draw that clear distinction between what is a direct effect of the ambient air versus what's the result of deposition. And so where we have drawn that is it will be become more clear, but where we've drawn that is to talk about the direct gaseous effects of the ambient concentrations under these direct effects sort of umbrella, and then to talk more about depositional effects, which includes, I think, what you're talking about more in the later conversation around those deposition effects.
Thank you.
Sure. Hans, you want to go ahead?
Yes, I just need some clarification here. When we're talking about vegetation, are we only talking about terrestrial vegetation, or where does the aquatic part of it come into play, or does it come into play?
So we will talk about aquatic impacts, but we'll talk about that through the deposition sections as opposed to the direct effects sections. But they're
okay. Okay, thank you.
Mm-hmm. I think this might be a good spot to take a break. The next section's a little bit longer, so maybe this is a good spot for a break.
Okay, let's do that. Let's take a 10-minute break. We've been at it almost 2 hours, so I think people need a break. So, the organizers can maybe put up a timer, and we'll come back in 10 minutes, which by my clock would be 58, whatever hour it is in your time zone.
I'm off mute now.
All right, the break is over. Are people ready to get back?
Okay, if we're ready to start. 1 second, we got reverb. Okay. Sorry about that. I'm not very good at talking over myself. Okay, so before we move into this section of the presentation, I just want to note that to make sure that we have enough time to get through the whole presentation, that I'm going to give just sort of a sampling, kind of an overview level of the types of impacts for both aquatic and terrestrial and nitrogen and sulfur that we looked at in the policy assessment. And you'll see in the document itself that there's tons more detail. There are appendices supporting the analyses. There's a whole lot more there than I have time to get through today. So I think what I'd like to try to do is I'll try to get through this whole section on aquatic, and then I'll stop for questions. But keep in mind though that we still have 4 more sections to try to get through, I think, in 2 hours to do it. So given that, I'll go ahead and get started. Okay, so like I said, what we're going to do is we're going to talk about how we looked at the aquatic impacts of sulfur and nitrogen deposition. And so we can go on to the next slide. Okay, so first of all, we want to recognize that there is an extensive and long-standing evidence relating nitrogen and sulfur deposition to impacts in aquatic ecosystems and through various mechanisms and various types of ecosystems. So there's a lot of information there. And so we're going to talk basically about 2 main groups of information. One is with regard to the nitrogen loading and its contributions to effects like eutrophication, algal blooms, coastal acidification, impacts in wetlands. And of course, we talk through the limitations and the uncertainties that we see in quantifying some of those linkages and the challenges in apportioning some of the atmospheric components of those loadings in some ecosystems between those that come from atmospheric deposition and from other sources. With regard to acidifying deposition, we also recognize, of course, that sulfur and nitrogen deposition contribute to the acidification in water bodies. We looked in detail at the information that was available, and we did some analyses. And so under current conditions, information, including those analyses, suggested to us that there was a much reduced role for nitrogen in acidification. And so one of the decisions that we made was in this review, we're going to focus on the assessment of the role of sulfur deposition in acidification. And we're going to do that through looking at specific targets for acid neutralizing capacity, which we'll talk more about in just a minute. So next slide, please. Okay, and so this slide's just intended to sort of summarize the approach that we're taking to aquatic acidification impacts. And so we wanted to sort of acknowledge the fact that, again, this is a really old body of knowledge. There's a lot of information about acidification of rain and surface waters and the deposition relationships with those in aquatic ecosystems. Particularly in the 80s and the 90s, we had a severe level of that where 25 to 50% of the assessed water bodies were showing significant impacts from deposition that at the time exceeded 20 kilograms of sulfur per hectare per year. Of course, the situation is a lot different now. Aquatic acidification was the primary focus also of the last review when we looked at secondary standards for NOx and SOx. And I don't think we've made it perfectly clear, but we didn't really fold in PM in the last review. So when we talk about the last review, it was just for NOx and SOx. And we acknowledged, of course, that the changes in water quality impact aquatic life and can mediate the biological response to both nitrogen and sulfur deposition. And while we looked at the effects of nitrogen and sulfur deposition on pH, we're using acid neutralizing capacity as our surrogate for pH. And we acknowledge that those changes can harm aquatic life. And so we'll move on to the next slide, please. Okay, so as in the past review, the evidence does continue to support our ability to do quantitative analyses to try to characterize these potential impacts and the associated deposition levels with those impacts. And so again, for this review, we focused on sulfur deposition, and we based it on analyses that indicated that there was a diminished role for nitrogen in contributing to acidification. So there's much more detail in the PA about that, and that you can read about how we made that decision. We've also used established water quality models to estimate the extent to which water bodies would be expected to reach ANC targets of interest across a range of sulfur deposition levels. And again, for the purpose of this review, we used ANC as the surrogate for pH because it was easier for us to model, and it's commonly used that way. And so for our analyses, we looked at 3 spatial scales. We looked at the national scale, we looked at the ecoregion level, which we used the Omernick level 3 ecoregions, and we looked at the case study scale. And for those 3 scales, what we also looked at 5 3-year time periods and 3 ANC target levels. And we'll get into more details of that on the next slide. Next slide, please. Okay. So the 3 ANC targets that we used were 20, 30, and 50 microequivalents per liter based on the available data and evidence that we had to relate the potential welfare effects that we associated with each level. And this slide just kind of gives you a summary of that, of the rationale that we used to select those. And this was also done in the last review where ANC was also considered relevant. And we looked at both long-term base load aquatic acidification protection, as well as episodic acidification and the potential for reducing time for recovery in some water bodies. And again, all of this is available in great detail in the policy assessment itself. Next slide, please. Okay, so this slide's just to give you a sampling of the results and conclusions from the aquatic acidification analyses that are included in the policy assessment. And one of the things that was important to note is that sulfur deposition has declined significantly since the last review in 2012. And under current conditions, few water bodies are estimated to be receiving sulfur deposition in excess of their ANC target critical loads. And so in this way, our analysis focused on the extent to which water bodies in sensitive ecoregions were estimated to achieve the various ANC targets that we talked about across the range of sulfur deposition levels. And so I'll give you just sort of an example of the kind of results that you are likely to see in the policy assessment. There's lots more, but for example, at or below 5 kilograms of sulfur per hectare per year, when we looked across water bodies, we found that about 90% of the water bodies in a particular ecoregion were estimated to achieve one of those desired ANC targets of 20, 30, or 50 in about 96, 92, or 82% of the ecoregions that were studied respectively. So we also looked at case study results and we had similar findings there. And so basically we took those results then and we talk about those results in the context of the range of sulfur deposition that is considered to be protective of the effects that we were concerned about. So next slide. Okay, so that was a really quick overview of the analyses and the information that was considered for the analyses in the policy assessment. And if we have any sort of general questions, I'd be happy to answer those now. Okay, well, so that said, let's move on to the terrestrial effects. Oh, I'm sorry.
Yeah, I had a question. So I guess my question was, you looked at acidification and you focused on sulfur. You didn't look at oxidized nitrogen. Was there any consideration for nutrification and looking at reduced nitrogen?
Yes, and there's a lot more information on that in the policy assessment, but we didn't do a quantitative analysis using that information.
There's a justification for that given in the policy assessment?
Yes.
Okay, I'll read it. All right, thank you.
Okay. Okay. Okay, so let's move on and talk about terrestrial effects. Okay, so again, we're just going to do a sampling of the associations that we looked at with regarding nitrogen deposition in terrestrial ecosystems. We noted that, of course, that acidic air pollution has been documented in terrestrial communities, including severe effects on growth and survival of sensitive plant species, as well as damage to lichen species and communities for quite a while. And there's a reasonable amount of information, evidence-based, to consider for that. We also looked at just nitrogen deposition because of the unique effects of nitrogen deposition in nutrient enrichment of these terrestrial ecosystems. And there's a wide variety of effects that can be caused by nitrogen deposition on growth, and it can lead to the alteration of plant communities and plant composition, as well as changes to biodiversity. So there are some recent studies that were available that we also looked at in depth, associating the differences in, for example, tree growth and survival, plant and lichen community composition over a range of nitrogen deposition levels. That's all in much further detail than I can present here, of course, in the policy assessment. So you should look for that. We're interested in getting your feedback on those decision points. And overall, the impacts of nitrogen deposition are widely variable, and they're subject to varying interpretations with regard to their role in affecting public welfare. And that was one of the challenges with this review, is that there's a large variety of impacts from nitrogen deposition over different ecoregions and ecosystems, and that not everything responds in the same way. So there's a challenge there in how we interpret that information. Next slide, please. Thanks. Okay, so here I'm just going to give you sort of a sampling of the assessments that we looked at with regard to the role of nitrogen deposition in terrestrial ecosystems. For example, there's a recent national scale analysis that reported associations for growth and survival impacts to many tree species across the US. There's also information about urban shrub communities and to some extent about lichen communities. And so there were large data sets there that we looked at and large analyses that we looked at to draw information for our conclusions in this section. And as well as, for example, information about lichen communities, which I think someone brought up earlier, and associating declines in species richness in lichen communities with nitrogen deposition. Next slide, please. So then we looked at sulfur deposition in terrestrial ecosystems. And so with regard to sulfur deposition, we note that sulfur deposition contributes to soil acidification, which can, of course, negatively impact terrestrial species as well as ecosystem structure and function. And there are recent studies that have found associations between reduced plant growth and survival across a range of sulfur deposition levels. And we look more closely at that. And there is the potential for these types of impacts to be influenced by historical deposition across the country, which is also a factor that we had to take into account. That the legacy of long-term sulfur deposition in certain parts of the country is still causing problems with that sulfur being released from ecosystems from past deposition. And so just to give you sort of an example of the kinds of results that we talk about in the policy assessment here, there are negative associations between sulfur deposition and tree growth that have been observed for sensitive tree species across a range of median sulfur depositions across the US. And though the sort of the median values for that were about 5 to 12 kilograms of sulfur per hectare per year. Again, you'll find many more details in the document about that. And so on the whole, sulfur deposition ranges did tend to overlap those that were identified for the aquatic acidification impacts, which was important to consider when we talk about our policy considerations and our policy options. And so that concludes the terrestrial section. So if there are any questions on that, I'll be happy to answer those or pass it to someone who can. Okay, well, with regard to that, then I'm sorry, Praveen.
I was going to ask you, I keep on hearing about this document. How big is this PA document? I'm just curious.
Well, in the history of EPA documents, it's not that big.
Tell me. How many pages?
Maybe 300 to 400.
Okay, thank you.
Including the appendices. About 300 to 400 pages.
All right, no, that's good news.
It's not 1,100.
Yeah, I know, that's what I was thinking.
Okay. All right. So now I'm going to hand it over to Pat to talk about the challenge of relating air quality concentrations to deposition.
Great. Okay. Okay. We've tried something new, so we didn't have to hand off computers, but we're figuring out a feedback issue here. And we found an old-fashioned solution, which is just to remove the computer from the room. All right. So as Dr. Schwartz identified at the sort of initial stage of this discussion today, one of the foundational elements here is how can we relate these air quality how do we relate deposition to air quality concentrations in the context of the NAAQS review setting process. Apologize, I'm fiddling with the screen here. Okay, so Deirdre introduced this plot before. Now we're in the yellow space, having walked through sort of the gray space. And so I'm going to just provide a really quick introduction to the policy assessment's description of how we took both air quality measurements and deposition estimates, as well as an internal analysis that we've done here using a trajectory-based model to estimate certain spatial relationships, and taken both of those two analyses and built a conceptual understanding of the relationships between sulfur and nitrogen deposition and various concentration metrics. Again, this is going to be pretty high level with more detail in the PA itself. Next slide, please. Super quickly on this one, if there's one takeaway, I think it's intuitive, is that the relationship between air concentrations and depositions is highly variable. It varies by pollutant, it varies by location, it can vary by time of the year. And as we talked about earlier, measuring some of these levels and making deposition estimates also full of a multitude of uncertainties. But just as a simple example, looking at a site in the Western US, potential location of interest from numerous ecosystems of the Sierra Nevadas, precipitation mostly occurs in the winter, especially this winter. Adjacent, mostly impacted by sources in California's Central Valley. Gas phase concentrations, particularly ammonium nitrate in that region, can be high. Most of the deposition in the Sierras tends to be from the dry deposition mechanism. Compare that or contrast that to a place in Shenandoah National Park in Virginia, where wet deposition precipitation can occur in all seasons. Source location probably is predominantly metropolitan areas along the industrial Ohio Valley and metro areas in the mid-Atlantic. Air concentrations in the park itself can be quite low, and more of the deposition there is from wet deposition. Just a sort of cursory example of some of the ways in which this relationship between air concentration and deposition can vary. Next slide, please. So again, restating some of this, an important part of the review is the consideration of this relationship. And, to the extent that we can characterize it, that can help inform decisions regarding which air quality metric might be best suited for any, revised standard intended to protect against nitrogen and sulfur-related deposition effects. We have attempted to build this characterization using two different analytical approaches. The first is we looked at a limited set of sites in Class 1 areas where we had co-located air quality and deposition data. So whether the air quality data was from CASNet or Improve, in all cases, the wet deposition data was from the NADP NTN network. We looked at, I think it was 27 sites as shown in the figure in the upper right. Certainly one limitation of this part of the analysis is the majority of the sites were in the Western US as opposed to in the Eastern US. But for these 27 sites, we looked at the relationships between various air quality concentrations, whether it was SO2 or sulfate or total sulfate or NO2 or nitrate or total nitrate or some of the intermediate species, and tried to ascertain whether there were statistically significant relationships between that air quality metric and the wet deposition of nitrogen and sulfur, or the combination of the two, at these 27 locations. And I'll provide some summary results in a subsequent slide. That was analysis approach one. The second approach we used was an attempt to extend this more nationally, as well as to bring it into more of NAAQS relevant space, that is design values. So in this second analysis, we attempted to identify for each of the 85 ecoregions that Ginger just teed up, what was a potential zone of influence for air quality emissions to impact that particular ecoregion. So we used the high split trajectory model and some rules of thumb that we identified to develop these zones of influence. And then from there, we looked at the air quality in two different ways within this zone of influence to try to understand what was the both average and the relationship between average air quality in this zone of influence and worst case air quality in this zone of influence, and looked at the relationship between those two terms and the deposition data in the particular ecoregion. And there, just to simplify the analysis, we looked at sort of median levels of deposition within the ecoregion. This will become more clear, hopefully, in subsequent slides. We do have an entire chapter on this in the PA, as well as an appendix on how we did the high split trajectory modeling. But just to leverage the plot in the lower right a little bit here, the area in whatever color that is, lavender, is an ecoregion 3 area that extends from northern Alabama into parts of southern Ohio and southern Indiana and parts of central Kentucky and central Tennessee. And each of the red circles there are air quality monitors that currently collect valid design value data. And we've done this individually for each pollutant. And our analysis suggests that those monitoring locations are potentially representative of air quality that might lead to deposition in the ecoregion, whereas the gray circles are not. So for that universe or subset of red dots, we would look at the air quality in that region and see what sort of relationship there is across that monitoring subset, those subset of monitors, and the ecoregion itself. Next slide, please. Okay, we'll start with the first approach, the co-located site analyses in a limited number of Class 1 areas. And I really want to credit a colleague of ours, Rob Pender, who's currently stationed in our Office of Research and Development for doing the bulk of this work. And this plot is complicated, but I think there's some value in walking through it somewhat slowly. If that's good with the panel, cut me off if it's not. So the co-located site analyses looked at 3 basic comparisons. First, we looked at, and again, it varied by site, either improve or CASNet air quality data or CASNet air quality data against the wet deposition from the NADP National Trends Network. That was sort of our starting point, was just with the observations that we have and only on the wet side, what is the relationship between concentrations and deposition? Second, we have CMAQ simulations for a number of different years. We looked at, well, just within the model itself, where we can get away from some of the measurement uncertainties, what do we understand about the relationship between air quality and total deposition within the model itself? And also within CMAQ, you can look at both, you can look at total deposition, you can include the dry deposition term. And then a third part of this analysis, again, we look back at the improve and CASNet air quality data collected at these 27 locations, and compared it against the TDEP estimates of total deposition, which again are a hybrid monitor model combination of approach to building a total deposition estimate. So the figure on the right shows multiple scatter plots for 3 deposition variables. So if you look down sort of a diagonal from upper left to lower right, you'll see the 3 deposition variables that we're considering here are total, N plus S, then S deposition alone, and nitrogen deposition alone. And then we look at the relationship between those 3 deposition variables and 5 different air quality measurements. So again, going down the diagonal here, first CASNet total nitrate, which is HNO3 plus nitrate, or sorry, first CASNet nitrate, just the NO3 radical, then total nitrate, which is NO3 plus nitric acid, and then CASNet sulfate alone, total sulfur, which is SO2 plus SO4 in the CASNet, and then all the terms combined is now we're at the lowest rightmost box. So in the diagonal, this particular illustration shows the histogram of the data set itself, whether it's deposition or air quality. But I really want to call your attention to the, if you will, southwest or lower left half of this multiple scatter plot matrix. And that shows for each pairing what the relationship is between, a scatter plot for each of those pairings, sort of showing the relationship. So let's just hone in on one in particular here as an example. So let's look at sulfur deposition, which is the second column, excuse me, in the plot. And then let's see how that correlates to sulfate, which is the 6th row, and total sulfur, again, sulfate plus SO2, the 7th row. So I don't know, you obviously can't see my finger here, but hopefully, that's the only way I can do it. You can sort of match those 2 terms up and look at the scatter plot for that individual case. So comparing sulfur deposition to CASNet monitored sulfate, you can see that most, if you're following, most of the plots tend to be a little bit above that red best fit line. There's not a lot of correlation when the deposition values are low, but there is a tendency, generally speaking, to as sulfur deposition levels get to a certain point where you see some weak relationship or some relationship, excuse me, between as deposition increases, that's associated with higher levels of sulfate. If you can match the correlation for each comparison is in the upper right part of the plot. And so for that particular pairing, sulfur deposition and CASNet sulfate, we see an R correlation value of about 0.87, which is one of the stronger ones. Let me pause there for any questions, and then we'll show one more example and go from there. But any sort of fundamental questions about the plot itself? Yes, Stephen.
Yeah, thanks for getting to this topic, which you recognized was of some interest to me, and I think probably a lot of people here. You're relating a local air quality measurement to a local deposition. Is that correct?
Correct.
And the deposition is, if it's wet deposition, it's as measured in a bucket. But if it's dry deposition, my recollection on this matter is that the dry deposition is calculated from the local air quality with some kind of a deposition velocity. So to the extent that the total deposition is going to be influenced by the calculated deposition from a concentration at the same local site, isn't that plotting X against X? And don't you immediately get a correlation coefficient of 1?
let me step back a little bit and just refer back to, we've sort of done this 3 ways. So the first is we've looked at local air quality against the local deposition in the bucket, the wet deposition. And so we have a series of plots there. And then, we've done the same thing on the CMAQ side. Let's just skip past that for now. The third sort of comparison here is we've looked at the local air quality as measured by Improver CASNet and compared that back against the total deposition, the TDEP data of sulfate and nitrogen, and then the 2 terms combined.
Yeah, which is the sum of the wet and the dry.
The sum of the wet and the dry is for both for sulfur and nitrogen in the TDEP yields, but in the
for one species, say sulfur, the total dep is the sum of the wet and the dry.
In the TDEP field, yes. In the NTN data, the first sort of series of these comparisons, it's just the wet.
Okay. But when you're considering the total dep, which is the wet plus dry,
right?
And the dry is calculated as some deposition velocity times the concentration. If the total were dominated by the dry, then you're plotting X against X.
No, I maybe I'm missing something fundamental, but the Y here is always the Improver, the CASNet, at least in approaches 1 and 3 here.
Yeah, it's a concentration.
Correct.
And the X is a depth, if I understand.
It is.
Okay. So if let's suppose there was no wet for the moment at some location, then the dry depth, which is the total depth in that case, is calculated from the local air concentration by a depth velocity.
Yeah, I think there's 2 things going on here, and any colleagues in the room can definitely weigh in as well. I'm not sure the hypothetical of all dry is something that we see very often. And then the second would be in the TDEP data itself, between some of the spatial interpolation that takes place and the weighing of the monitored values versus the modeled values and some of the bias correction that takes place. I'm not sure you would ever get a perfect 1-to-1 relationship there either after you've sort of reconstructed the deposition, even the dry deposition term, using the TDEP approach.
Okay, so you're saying it's a broader concentration field or something like that.
Well, it's a even at the point of the measurement, the TDEP field is not going to be, tell me if I have this wrong, Colleen, but I don't think it's going to be a 1-to-1. The TDEP field is necessarily going to exactly mimic that particular observation. But
But just to clarify, the dry depth is modeled on the basis of some concentration. It may be a concentration field that comes out of a model, as opposed to the local measurement, times a depth velocity.
Correct.
Okay, I understand, and I'm raising a concern. Let's not get to it now.
Yeah, we will have lots of time to deliberate in a few weeks.
So we look forward to the conversation. Yeah, I'll stop there.
Yeah, me too.
It's a détente. Any other, thank you for that. Any other comments or questions about the figure itself?
And Bill McDowell has his hand up.
Yeah, I was wondering if you could speak briefly to the odd data distribution where there's bifurcation or 3 seeming regressions plotted. For example, if we look at that S deposition column and the second graph down.
Mm-hmm.
I don't know how does that get generated and what does that mean?
I'm not sure we're looking at the same box, but we do see sort of modes of data in a number of these different scatter plots. The best example I could think of, and it might not be the one we've selected for this, is like when we're looking at PM 2.5 on the x-axis and how that compares to deposition. We know that in a number of different locations, organic carbon or elemental carbon or crustal or some non-sulfur nitrogen contribution to the total PM is significant. And so, whereas in other areas, sulfate may dominate the PM. And so that's the, that's not in this particular plot, but that's an example of the types of sort of modes of data. So I think ultimately it just sort of, comes back to the local air quality in that particular region that sort of drives some of these different modes of data that pop up. And I think in the PA, not exhaustively, but in a number of different instances, we try to call out the explanations for why we see, the patterns that we're seeing in these scatter plots. That wasn't a very complete answer, Bill, but hopefully that helped a little.
Yeah, thanks.
Praveen, did you have a
Thank you. Yeah, quickly, Pat, I'm just looking at the scales of these charts, horizontal scales, and also vertical. What exactly are these? Air quality and deposition, and what scales?
Yeah, it really takes some time to parse them out. But so let's look at the in deposition row, if you will. So the x-axis there, the units there are kilograms of nitrate per hectare year.
Per year.
Yeah, and then if you want to compare that to any particular concentration value, let's take CASNet total nitrate. I think these were done in ggplot, but the axes, the x-axis, or excuse me, the y-axis sometimes are on the left and sometimes are on the right, just for visibility purposes. So total nitrate, if you will, following that to the right, the units there are micrograms per cubic meter. Yeah.
And what are the vertical scales then?
Well, they vary by each term, but that's the concentration.
I think part of the point is the vertical and the horizontal scale is the same for any particular, is that correct?
Yeah, so you have to sort of focus on a particular row and a particular column. So let's look at the CASNet nitrate, TNO3. To find the y-axis there, which are going to be in units of microgram per cubic meter, I think you would look to the left there. But then when you're relating that to any particular deposition, the x-axis then would either be at the top or the bottom. Yeah, I apologize. This is a little bit convoluted, my description here. In the PA themselves, we have very detailed captions, I think, that can point people to the scale that we're evaluating and the units of the different terms. I apologize for muddying that.
Thanks, Pat.
Okay, why don't we try one more example here, which is nitrogen deposition. Aaron, if we could go back just real quickly. For nitrogen deposition, so now we're looking at the third column here, and let's look at how that compares to total nitrate, which is the CASNet TN term. So you can see the scatter plot, not a lot of deviation from the best fit line. And if you're following along here, the correlation there is 0.85. But what's interesting about these plots, I mean, our primary takeaway here is trying to determine which sets of relationships have very little correlation, might have moderate correlation, or strong correlation. So the PA walks through dozens of these types of plots and calls out where we think, based on this limited co-located set of sites in class 1 areas, we see some local to local relationships. Some cases we do, in many cases we don't. And that's what we're trying to summarize in this first approach of relating air quality to deposition. Now, maybe moving to the next slide, we can talk about the second type of analysis that we did, which is the zone of influence analysis. So again, we have a whole appendix in the PA that describes the high split work that we did to develop these zones of influence. At their core, we're using 48-hour forward trajectories with a release height of 500 meters, which we hope to be representative of releases within the mixed layer. And we're using a single year of meteorology, 2016. No single year can really be deemed representative, but we will note in terms of like the INSO cycle, this was a pretty neutral year. And so what we're hoping to do again here is to understand what subset of upwind monitors might potentially contribute to deposition in a downwind ecoregion. We made a subjective determination, this can certainly be debated, that in order to be included within the zone of influence, 1% of all trajectories that entered into that ecoregion had to be tracked back to that monitor starting point. As you might have picked up from the one sample we plot, this resulted in relatively narrow zones of influence. If you look back at that Tennessee and Kentucky plot, we're not, having monitors from, the Dakotas or Florida as part of a zone of influence for that location. Most of the sites are either in the ecoregion themselves or within about 100 kilometers of that ecoregion. And so then what we did once we identified the zones of influence, we looked at the design values for each of the monitors within that zone of influence and looked at how they related to deposition within the ecoregion. Again, looking at the ecoregion's median deposition value. We looked at this two ways. We did a weighted average, which was an attempt to more highly value those monitors that more often contribute or more off their wind trajectories intersect with the ecoregion, and weight less strongly those monitors where the impact was likely less frequent. That was one approach. The second approach was to, for all the contributing monitors in the zone of influence, just simply identify the max design value. So again, the PA has scores of comparisons of various concentration terms and deposition terms in this zone of influence space. We've just looked at one example here that I'll try to walk you through. So the x-axis, well, let me start with the y-axis. The y-axis is the sulfur deposition averaged over 5 3-year periods, the same 3-year periods that Ginger discussed earlier, where each time period is color-coded. There's a different color for each circle. And so that's the y-axis, is deposition. And then the x-axis is within the zone of influence for each of these ecoregion time periods, what was the weighted annual average SO2? This particular example isn't in design value space, but obviously for the NO2 secondary standard, which is an annual mean, we have it there. We also have plots here for weighted second highest 3-hour. But this particular example, we're looking at annual average SO2 in those 3-year periods and attempting to relate that back to deposition. So there's pretty strong correlation between the weighted zone of influence annual average SO2 and total sulfur deposition. That's our takeaway here. Once you get past a certain point, particularly for deposition levels greater than 5 kilograms of sulfur per hectare per year, or particularly once you get past SO2, higher than SO2 values than, say 2 ppb from a weighted average perspective. Bill, to your question earlier, we sort of see a couple different modes here. I think the lowest mode where we have high annual average SO2, but relatively low sulfur deposition. I think our hypothesis for that one in the PA is that those are probably sites that are more closely located to a particular industrial source, to where all the contributing sites in that to that ecoregion are perhaps more influenced by source-oriented monitoring than you might see in another region. I know there's a lot there, but I'll pause for any questions. Then we're gonna, I think, wrap up this section. Yeah, Bill.
Yeah, this is much easier for me to follow than the previous, all the data together. To me, this is pretty compelling, but it raises a question that I don't think has been addressed on the slide or in your comments yet. To me, the lack of predictability in the recent years, the lower brown corner, the lack of predictive ability from SO2 to total S deposition, it's the brown blob.
Mhm.
It seems then that it sort of weakens the ability to say to what extent changing air chemistry will result in changing deposition. And is that addressed in the PA?
It is, and others here may be able to speak to this better. I think, Karen, you're taking the next section. We'll talk about it a little more as to, how these analyses inform some of the decisions that we're, that the administrator is going to have to make here. But we sort of see it two ways. We agree that, looking at the most recent data and the very low sulfur deposition values that we see these days, that the lack of a relationship is challenging. We do think there's some value, and one of the fortunate things about doing an analysis like this in a period of changing air quality is that it enables us to understand the relationships in other space as well, i.e., what we used to experience, and we think that's meaningful still. That the relationship exists at certain levels and then maybe starts to break down at others. So we've sort of encompassed both of those parts of the curve into attempting to inform any sort of decision making as to what air concentration metrics might be useful in a next standpoint. So I don't, again, an imperfect answer, but I think both takeaways there are helpful. I think I saw Frank and then Rich. You're muted, Frank. Frank, sorry, you're on mute still in the Zoom.
I thought the phrase that was begat by COVID, you're on mute. Anyway, so I agree with what Bill was saying about the scatter of these points, especially as you get toward the end of the sample period. Have you considered maybe doing like centroids, maybe like two-dimensional means for each of the 5 periods, and to look at like a trajectory of change over time? I was just wondering if that might add to some interpretability. Does that make sense? So you would have a single two-dimensional mean for the 01, 03 period and so forth, all the way down to 18 and 20.
Yeah, that does make sense. I think, this and the sort of co-located analyses, I think there are a number of different ways in which those data sets could be evaluated. And, we are certainly interested in any input as to alternate ways of doing it.
Okay.
So yeah, that'd be perfect. Yeah, Rich.
Right, sort of a two-part question. I wanted to first understand the concept of in order to be a NAAQS, it has to be something measurable in the ambient air, but the effects of concern here are largely through deposition. So can we have a NAAQS, therefore, that might be based on a component of PM, or for that matter, a combination of gaseous and particulate measurable sulfur? As I recall back from the 2008 proposed acidification index, that was going to be how part of the measurement was sort of total atmospheric sulfur, which was some combination of SO2 gas and SO4 particulate matter, and a similar construct with total atmospheric oxidized nitrogen. So that's the first part of my question. Could a NAAQS be based on some combination of components of two criteria pollutants? Part one.
Maybe we'll tackle part one first. I'll go ahead and try to address your question. So is basically yes. I mean, so the NAAQS are for, at least the ones we're looking at here, are for oxides of sulfur, oxides of nitrogen, and PM. And the current indicators are SO2, NO2, PM2.5, and PM10. If in this review, we felt that it was more appropriate to have a different indicator that was measured, then one could establish a new or a revised standard with that new indicator. I think one of the things, and I'll talk briefly about this in the next set of slides. One of the things that has to be kept in mind is that with a new indicator, one must also assess the reference method by which that indicator is measured. So we would, especially if it's not one of our typical ones. And then second, one would need to also assess at what monitors that metric or that indicator should be measured and where those monitors should be placed. So it gets, it's a lot to it. It's complicated. So
okay, I get you. So, and then part two was going to be, just for example, maybe a more useful question for this graph would be weighted average total atmospheric sulfur, some combination of SO2 and SO4, since we know that particle phase SO4 and wet deposition of SO4 correlate relatively well. Just, looking at this, but in a more detailed way, using our understanding of what these relationships between the gaseous and particle and deposition components are.
Right. Yeah. And I'm not sure if it came across clearly, but one of the things we're trying to do in this analysis is think about a monitor that's stationed near a source where
Oh, Karen disappeared.
I'm not hearing anybody.
Yeah, EPA is still there. Oh, there you are, Karen.
Okay, so sorry, the computer just did something. So sorry. I think the question was about SO2 and SO4, and I was trying to get into some detail with respect to what the policy assessment does. And this first analysis, the second analysis that is up on the screen is trying to relate SO2, is trying to relate monitored concentrations that are generally going to be in spaces that are higher in SO2 to areas where sulfate has been transported and will mostly be dominant in SO4. So that is like the underlying premise in looking at this and relating it to the sulfur deposition there. It's not perfect. The first analysis that I think was very educational to us all, with Pat walking through that very complicated metric. That analysis specifically was trying to look at in co-located areas where you have multiple different types of measurements, including deposition, what types of indicators correlate well with deposition. And the attempt of the policy assessment is to pull those two analyses together, while not necessarily either is sufficient alone, but to pull them together and look at those relationships together in informing a potential standard. Okay. Good.
Praveen, yeah. Yeah, thank you. I'm just trying to get an idea of this word, zone of influence. So I'm thinking it's like an area, upwind area, the scale of that area? Is it hundreds of miles? Is it also really the thing you're going to do in policy assessment where you decide something needs to be done at some places and then you look where it would be done? Is that the way? It's like a modeling, CMAQ type modeling, looking at where the sources are.
Yeah, and I don't know, Aaron, if you can go back to the previous slide.
I mean, you had a picture before that, you know, a color, pink color or lavender color. I thought that was the zone of influence.
Aaron, can we go to 44? Thank you.
Yeah, that thing.
Yeah, so first off, just stay up front, reiterate something I think Erica said in the ground setting, which was this is in no way a signal towards implementation space. This is just an attempt at, as Karen just suggested, I think a helpful construct here is the first analysis is sort of local to local. This analysis is more focused on upwind to downwind. And so in the red dots, those are the locations that would comprise our zone of influence. But what they really are monitors that have valid design values for whichever particular pollutant we're looking at here. And then that comprises the subset of data for which we evaluate the air quality to deposition concentration, the upwind to downwind. Doesn't look.
I hear you clearly. It's not implementation, but when this thing is done and policy assessment is done, and EPA and others trying to see what needs to be done and how much and where, that's where this zone of influence thing would come in.
Except it will do so in a different context. The implementation of secondary standards are, a unique challenge. One of the first steps in implementation space is sort of identify as prescribed by the Clean Air Act is, who contributes to pollution, in a given non-attainment area.
Yeah.
So, the designation and classification space that I think many of us are familiar with in context of the primary standards is a lot more challenging in secondary standard space. And I think it's way far past where we are now, which is just we're trying to better understand the concentration to deposition relationship so that we can identify metrics that air quality metrics that are meaningful in deposition space, or at least as meaningful as we can do given the various uncertainties and data limitations.
Okay.
If we're ready, Leanne, I think we can move into the next section.
Yeah, I think we need to keep moving or we'll run out of time. Thank you.
Thank you. Okay, so I'm gonna do the next 7 slides, and for the sake of time, I'm gonna get through all 7 and then take questions on those 7 as well as the entire package. Okay, so thank you so much. So we're going to step through some of the conclusions that you're going to see in Chapter 7 of the policy assessment. So with respect to SO2, SO2 is a criteria pollutant with the clearest ties to deposition-related ecosystem effects through its correlation to sulfur deposition and the role of sulfur deposition in aquatic acidification of water bodies that has occurred over decades. Based on air quality information, there is a clear relationship between SO2 emissions and SO2 concentrations and sulfur deposition. We found that the SO2 is the most prevalent gaseous sulfur oxide in the ambient air. It represents the vast majority of sulfur emitted. SO2 emissions generally come from large point sources, and SO2 monitors are generally placed close to those sources. Though through well understood chemical reactions, the gaseous SO2 is converted to sulfate components, which generally make up the majority of the sulfur deposition in rural areas of the US. And then also reductions in SO2 emissions result in reductions of sulfur deposition from both gaseous phase SO2 and particulate phase sulfate. From the trajectory analyses, examining the relationships with sulfur deposition, we find that either air quality metric that was assessed, we looked at the current form of the standard, the second highest annual 3-hour SO2 daily maximum averaged over 3 years. And we also looked at a potential different form of the standard annual average SO2 averaged over 3 years. And we find, based on the results, that either metric would be a metric that could be used in controlling sulfur deposition. We find that the annual average metric had a tighter, stronger correlation and might be the better choice. We also note that, as expected, there are notable variations in monitored SO2 concentrations across the US, and this does point to focus on ensuring that the highest monitors contributing to the sulfur deposition are reduced. Next slide, continuing on, as you noted, there's substantial scatter in the air quality deposition relationships, particularly below 5 kilograms per hectare per year of sulfur deposition. And this definitely contributes to the certainty in using the relationships for controlling sulfur below these concentration, below these deposition levels. I will also note that looking at the most recent time period, we have a real life example of where the sulfur deposition was maintained below 5 kilograms per hectare per year. And in that time period, the annual average SO2 concentration averaged over 3 years was below 22 ppb, and most monitors, in fact, were below 10 ppb. The policy assessment concludes that in looking at the range of policy options that are supported, that it would be appropriate to consider retaining the current secondary SO2 standard to protect against direct effects. But there is also support for considering revision of the current standard to increase protection against sulfur deposition related effects. Options that are included are revising the level of the current standard from 500 down to 200 to 400, continuing to be set as the second highest daily 3-hour maximum, and revise the form to be averaged over 3 years, or to establish an additional SO2 standard with an annual mean standard averaging time averaged across 3 years, and with a level between a range of 22 to 10 ppb. And if this standard were selected, to also consider revoking the current 3-hour standard, given the level of protection that this type of standard would maintain. So moving to NO2, while there's a clear relationship that we saw between in deposition and ecosystem effects, the extent of additional control needed to ensure adequate protection for terrestrial ecosystems from nitrogen deposition related effects, it remains unclear. The policy assessment analyses indicate the potential for protection from ecosystem acidification with a focus on SO2. The nitrogen enrichment impacts of nitrogen deposition are varied, are subject to varying interpretations, present difficult science policy questions. Nonetheless, based on a nitrogen deposition focus and depending on the weight placed on different types of studies, it could be appropriate to consider general control of nitrogen deposition levels to below 12 kilograms of nitrogen per hectare per year. In looking at that level and looking at the trajectory analysis, we find that when looking at NO2, the correlation that was between the annual average NO2 concentrations and nitrogen deposition tended to be somewhat low, calling into question how well a standard set based on NO2 would control nitrogen deposition itself, likely due to the fact that there are multiple components contributing to nitrogen deposition, not just NO2 by itself. And then second, correlation between an annual average PM 2.5 concentration and nitrogen deposition was much stronger. Again, likely due to the fact that multiple different components of nitrogen are being deposited, and those are many of them being measured with the PM 2.5 metric. So moving on, additional conclusions here. Therefore, a standard set as a PM 2.5 annual averaged over 3 years might be found to be more effective for controlling nitrogen deposition than an NO2 standard, and such a standard would also provide control for sulfur deposition. We note, of course, that this is not a perfect metric. We note that there are areas of the country where the PM 2.5 mass will have substantial contributions from non-sulfur and nitrogen species, and that may make it less ideal in those areas of the country. So the policy assessment does conclude a draft conclusion that it would be appropriate to consider retaining the current secondary NO2 and PM 2.5 standards to protect against direct ambient effects, but also consider revising, and those options could include revising the level of the NO2 standard to below 53 to as low as 40 ppb, and in addition, considering revising the PM 2.5 annual standard level to below 15 and to a level as low as 12. So this slide has a lot of information that's supported based on the first air quality analyses that was done. So this looked at, as you remember, that analysis looked at controlling sulfur and nitrogen deposition in class 1 areas and looked at co-located information. For sulfur deposition in rural areas tended to result primarily from deposition of sulfate and SO2, especially in the West, with more dominated by sulfate in the East. In looking at that analysis, there were multiple metrics measured at CASNet and improved monitors that did correlate well with nitrogen deposition. A sulfur deposition, here they're listed: improve PM 2.5, improve sulfate, as well as total sulfate measured at CASNet. And so all of these have the potential to be able to predict sulfur deposition in those types of rural class 1 areas. Similarly, for nitrogen deposition, the analysis also looked at those areas and co-located information. Nitrogen deposition in these rural areas was found to be fairly well correlated with air concentrations of nitric acid and inorganic nitrogen. There were multiple indicators as well: improve 2.5, improve organics, others that were measured at the improve as well as the CASNet sites that were found to have a good correlation with the nitrogen deposition, making them promising with respect to being able to correlate and predict with nitrogen deposition changes. As I think we've mentioned in some of the answering some of the questions, if we went a route of looking at this type of option for the secondary standards, we would need to consider multiple things. We would need to consider the design of the appropriate monitoring network in its location, as well as the number of monitors and where they're located, how many of them and where they're located. Additionally, as we also mentioned, we would need to, based on the metric and based on the indicator that we would be putting forward, look to see what federal reference method work would need to be done to ensure that there would be one in place to measure that indicator. And so given all of this, the policy assessment concludes that it's unclear whether this is an advantage to go this route versus the other proposed ranges that we put forward in the policy assessment. So I will just go to the next slide and won't stay on this long. This was included to have a handy place where in one place you can see the current standard levels as well as the potential ranges that are put forward in the draft policy assessment. And then let me just move to the last slide to close this out, and we can take questions. Generally, just to put forward, remind everyone, the administrator's decisions regarding secondary standards in general are largely public welfare judgments. Different public welfare policy judgments could lead to different conclusions regarding the extent to which the current and various alternative standards might be expected to provide the requisite protection. Of course, those public judgments relate to a variety of things, including identification of effects of public welfare significance, as well as the appropriate weight to be placed on different elements of the evidence and air quality information. And of course, how one considers the uncertainties and limitations associated with both of those things. And then lastly, the administrator's final decisions on secondary standards that provide the requisite protection of public welfare. Those decisions are based on the evidence, the quantitative air quality analyses, the exposure risk analyses, of course, advice from CASAC and public comments. So let me stop there. Those are all of our slides, and close and take questions.
Thank you, Karen. Does anyone else have any questions or wish to ask right now? Charlie.
Yeah, my question is more of a procedural question. So my understanding is that this analysis is based on the ISA, and the ISA was finalized in 2020 and included literature before that time. So in the intervening period, there's been a lot of relevant literature. And I mean, I understand that, you know, that there have been problems with this in terms of timing, but are you concerned about that there might be some important literature that might influence your decision if you had a more up-to-date inclusion of scientific information? So could you just generally comment on that?
Sure. And so in reviews, we do get to places where we have a final ISA and we haven't completed the review. And at this stage, you know, we do look to CASAC to voice any studies that they feel are critical and that should be included in the review. We also look for information from CASAC of why those studies are critical and in what way they might change or be incorporated into the policy assessment or even into the ISA if that is, you know, if they are indeed altering with respect to the ISA conclusions. And so, you know, that's a question that we're looking into CASAC to answer. I will note, as you saw in the intro slides, that we are under a tight schedule with the consent decree. And so if things rose to the level of needing to be revised in the ISA, that would be a decision we would have to seriously consider with respect to next steps and what that would mean, given that we have a legal deadline on our plates. So.
Okay, but we could bring critical articles to your attention if we thought that they were appropriate.
Yes.
Yeah, thank you.
You're welcome.
Hans. You're muted, Hans.
I'm muted. Gosh, I haven't learned in 3 years of doing this. I have a question about it's a geographic question, really. So how far are we to consider impacts in the aquatic environment going into estuarine and coastal systems? I didn't really hear much about that, and I'm wondering whether there's discussion of that in the report that we're going to be able to see. And the reason I asked that question is because there's a lot of interactive issues there with regard, well, let's take nitrate, let's take the oxidized nitrogen route. You know, you have an issue with potential acidification, potential eutrophication. Those two could cancel each other out. It becomes a rather complicated situation, but we know those systems are very sensitive to nitrogen. So I'm just curious what the, how much coverage is going to be.
Right. And so let me turn to Ginger. We do, just to start off, we do consider all of the things included in the ISA. So all of the evidence that was included in the ISA, including those endpoints that you are raising. And then let me, I'll switch to Ginger to maybe offer you a little bit more detailed, specific response.
Okay. So as you raised, those are really there's some really complicated issues in there. And so the PA does address sort of all four of the sort of endpoints that we're talking about. We address acidification relating to nitrogen and to sulfur to the ability that we can within the evidence, as well as the impacts from nitrogen itself to both terrestrial and aquatic eutrophication or nutrient enrichment. It's the difference is our ability to quantify some of that information and the evidence base that's available to quantify that information, to look at sort of assessing risk that we think is attributable not only to deposition, but that we can not only apportion to deposition, but we can also talk about in the time frame of sort of the long-term exposures that we've had to both nitrogen and sulfur. So that stuff is in the PA, but there is a difference in our ability to quantify that information.
Yeah, but what about the coverage? Should we consider estuaries? Or is it only freshwater?
We do try to talk about estuaries. We talk a little bit about coastal acidification. In those systems, of course, we have some limitations. We have models that require very specific to locations, where you're talking about. The estuaries have their own data. And so it's very data intense. We don't have a whole lot of data to apply individually to estuaries around the country, but we do try to address algal blooms, and we try to address the impacts of inputs to estuaries, and we address just a little bit with the coastal acidification impacts. So as far as the evidence base goes, yes, estuaries, coastal acidification, other systems, wetland systems, those systems are all addressed in the policy assessment. We just have a varying degree of ability to quantify them.
Okay, thank you.
Sure.
Praveen, I think you're next.
Yeah, thank you. And I'm not muted, so that's good. I think one of the things you said in conclusions, revising level of annual NO2 standard to below 53, which is the current one, to as low as 40. So it wasn't clear to me how you got to that number 40. And number 2, which is coming from the previous assessment we did, this whole role of ammonia, the way I think EPA addressed it, then the language you had used, taking into account, those were the words, ammonia, without doing much about it, but taking ammonia into account. So I'm wondering, this analysis, how have you taken ammonia into account without really addressing what to do about it?
Okay, let me see if I can answer your 2 questions. The first one, I'm gonna, a lot of that is based on information looking at more direct effects from NO2. And I think I'll leave the final answer of that to your reading of that section of the document and for later in June when we see you in person for that discussion. The second question is, it sounds to me like it's related to ammonia, NH3, and how we treat it. And so I don't know if this is going to be helpful or not, or whether this is a point of confusion, but the NAAQS that we have on our plates to assess are oxides of nitrogen, oxides of sulfur, and particulate matter. And so those are the ones we're looking to see whether the current standards are providing appropriate protection. Ammonia, while it is a precursor of for ammonium, it is not a criteria pollutant.
Yeah.
Okay, so that just want to clarify that.
No, that's clear.
Okay, and so when we are looking at how one would be looking at the protection, then ammonium is being addressed through looking at the nitrogen contributions coming from components of particulate matter.
All right, got it. That's the way you're going to address ammonia through PM2.5 fraction, nitrate fraction.
And just to reiterate, I think what we said several times, of course, the implementation of these standards is beyond the scope of what we are doing in this review.
Thanks.
You're welcome.
Rich?
So I guess I sort of started to make this point before, but it seemed to me that all of the policy options that you were evaluating at the end there, summarizing, each was limited to a specific existing measurable criteria pollutant standard form, such meaning NO2, SO2, and total PM mass. But conceivably, there would be other combinations or mixes of those things, such as you did consider in the previous secondary SOx NOx review, things like total atmospheric nitrogen, including both gas and particle phase, and total atmospheric sulfur, including both gas and particle phase, or even a combination of total atmospheric sulfur and nitrogen, such as you did consider, I think, as potential measurable metrics in the last review cycle. So I guess I wanted to ask if those conceptually, if those kinds of things might still be options, part one.
Okay, so part one. It potentially was not clear in the slides. So the policy assessment is concluding that a standard set based on NO2 or SO2 or PM2.5 could be effective in controlling deposition of nitrogen and sulfur across the U.S. and in particular in rural class 1 areas. Second, the policy assessment concludes that another option, another way, another potential range of policy options on the table would instead be to set a standard based on various different indicators that we've looked at, including ones that were total measured sulfur or total measured nitrate in areas, in rural areas, in class 1 areas, based on monitoring networks that are there. And the policy assessment notes that in doing so, one would need to evaluate what a federal reference method would look like, what those measurements would look like, what those monitors would look like, where those monitors should be placed, and so forth and so on.
Okay, thanks. That actually leads right into part two, which is that, again, at the end of the last review cycle, CASAC had recommended and EPA had agreed to establish a pilot monitoring network to evaluate the proposed methods that were going to be deployed last time, which involved these combinations of gaseous and particle mixed pollutants and so forth. Never really went very far. And then I recall one or two sites that I know have since been discontinued. And that also reflects an additional discontinuation of other CASNet sites. And early on in the presentation, somebody pointed out that you're limited by the data that's available. And I think somebody also maybe mentioned that CASNet itself is currently undergoing a review, and there are other information needs that might be considered, and budgets are limited, and we're stuck with the monitoring network that we have or we can afford. So it seems to me that kind of thing should be taken into consideration at the same time as we do this NAAQS review. Not only to what extent are we able to maybe even propose or consider a standard, but to what extent do we have the relevant information to consider these kinds of relationships going forward into the future?
Yes. Well, that was easy. I agree. And in fact, one of the requests of the Clean Air Act of CASAC is to clearly articulate research needs and things along those lines. So while appropriate for the review, please also keep in mind those are the types of reactions and inputs that we look from CASAC to CASAC for as well.
Jim.
Yeah, I had a question maybe for Karen. So for the SO2 options, the 200 to 400 ppb not to be exceeded more than once per year, or the 10 to 22 ppb annual average, does the policy assessment go through an analysis to show which one would be more restrictive? Or, I mean, because it's hard to just look at those two and think about what it really means. Is that type of analysis done in the policy assessment?
I don't think to the extent that you're looking for or asking for. No. It does consider how well each of those two metrics corresponds to a deposition, and a sulfur metric, SO2 metric that's limiting peak concentrations, particularly when you have very high monitors or areas across the country, does not prove to be a poor choice because of those relationships between the SO2 concentrations and the sulfur deposition. But on the other hand, because sulfur deposition in the way that we are assessing it is really accumulated and the effects that, over a longer period of time, what we found is that the relationship between what an annual average SO2 concentration can maintain with respect to accumulated sulfur deposition, it might be a more effective choice just based on that relationship alone. And that's what's more there than is one more stringent than the other.
Yeah, that's helpful. And I think you said earlier that was EPA recommending the annual over the 200 to 400 not to be exceeded. Is that actually in the policy assessment that the annual might be the preferred?
Yes, I mean, we try, to put a range of policy options on the table, especially, looking for CASAC input on those options. But you will notice in the policy assessment wording along the lines of there's a better correlation and it might be a better choice.
Yeah, makes sense. Thank you.
You're welcome.
Stephen, you had a question.
Yeah, you seem to be presenting policy or policy options as or this standard or that standard. Could a policy option be and not to exceed this and not to exceed that? So that some of it protects in one way and some of it protects in the other way.
Yes, exactly. And, we are looking at both direct effects as well as deposition effects. And I mean, one could even see a place where you would arrive where the standard that you think should be in place to control high peak concentrations versus the standard that you think should be in place to control accumulated deposition may not have the same type of control. And you might want both. Of course, the same is true across pollutants. So the simple answer to your question is for sure.
Good. I think that opens the door a bit in terms of my thinking, because you have local temporary acute sort of problems from a high concentration affecting plants this way or that way. And you also have the more chronic issues associated with deposition that's going to accumulate in some sort of a watershed. And so I think in terms of protecting ecosystems, which is one of the objectives of the secondary standards, I think it shall not exceed this and shall not exceed that. It could be a valuable approach to meeting both of those objectives. Thank you.
Any other questions or comments for EPA?
I just have a comment for the gentleman who presented those zones of influences. I think because of geometry, the further away, just because of geometric considerations, your probability of a trajectory hitting a particular place goes down as 1/r. And so therefore, in order to define your zone of influence, you really have to weight it by the distance from the place, and that's going to expand that zone of influence tremendously.
Thank you. And hopefully the policy assessment gives a little bit more information on that. But, just to quickly say, the zone of influence is characterized by the high split model, which takes into account meteorological variables and how like a particle or a gas would be transported based on those meteorological measurements that are input into the model, if that helps.
Yeah, sure. But the likelihood of a trajectory starting at some place distant from another place, just because of geometrical considerations, goes down as 1 over r. So therefore, to get an unbiased estimate of a zone of influence, you have to weight any of those percent likelihoods by the radius distance from source to receptor. And that's it's going to expand the zone of influence tremendously, which I think is appropriate because the residence time of the, especially of the aerosol constituents, and times the mean wind speed is going to bring you up to the 500 to 1,000 kilometer range, not something like 200 or 100 that he had in that map.
Okay, any other further questions or comments from members of the panel? Praveen.
Got to be unzoomed here. A quick question. Maybe you can tell us how are you addressing the uncertainty? I mean, the word was mentioned a number of times. Is there a full description of that in PA, or where are you with respect to that?
So within each section, there is a discussion of uncertainties and limitations in the evidence and the information. And in the conclusions, those uncertainties and limitations are also weighed. So
Thanks. I'm just very happy it's not 1,000 pages, 400 pages.
we'll make sure not to add any empty blank ones.
Any other questions or comments from anyone? All right, maybe we'll be able to close this meeting a little bit early. I wasn't so sure there in the middle when we were peppering EPA with all kinds of questions and comments. So before I turn it back over to Aaron, I wanted to thank EPA for your thoughtful and thorough presentation, and also to recognize the enormous amount of work that's represented by this presentation and the document that they've promised to send us tomorrow. It seems to me that this has been a very challenging task for EPA to complete, and we'll need to take that into account as we develop our advice at the June meeting. So, oh, there's a couple more hands up. Praveen, is your hand left over?
No, I'm done. Thank you. Sorry.
Okay, Donna.
Yeah, thanks, Leanna. I was just wondering about the charge question situation. Do we get those sometime soon? Or is that for the next round?
Yeah, so the document, the draft policy assessment will be accompanied by a transmittal letter, and that letter will have charge questions included.
Oh, okay.
So Don, yeah, go ahead.
Oh, I was just going to say, and then Aaron and I will follow up with assignments, but we will not do them instantly. It'll take.
Well, it'll take a little time to read anyway, so there's no immediate hurry.
Yeah, but that'll come pretty soon. I guess we're ready to turn it back over to Aaron then.
Yeah, so just a few points. You should have been contacted by our travel staff already. For those that will be attending the June 28th, 29th meeting, please take care of your travel arrangements, as well as a reminder that the hotel cutoff, I think, is June 8th. So please take care of that as soon as possible as well, to be able to get that group rate there. And then, as Leanne had indicated, we will follow up once the document comes out as well as the charge questions. We will send that out to you. But then it may take us a few days to do the charge question assignments as well as further details and assignments for the meeting. So we'll be in touch. Okay, with that, I think we can adjourn the meeting. Thank you, everyone. We'll be in touch and we'll see you in June.
Thank you.
Thanks. Bye-bye.
Bye.